Hello there, and welcome to Physics with William, where curiosity gets comfortable and difficult ideas are invited to sit down quietly for a while. Tonight we're easing into one of the strangest meeting points in all of physics, a place where two of our greatest descriptions of reality stop politely nodding at one another from across the room and begin to disagree in a rather serious way. The subject is the Planck mass, which may sound at first like a forgotten unit from a dusty textbook, or the sort of thing one might pretend to understand during a university seminar while secretly hoping nobody asks follow-up questions. But it is far more interesting than that. Hidden inside this idea is a boundary, a clue, a pressure point in nature itself. It marks a scale where gravity, usually so calm and weak in the world of particles, can no longer be ignored, and where quantum physics, that unruly master of the very small, begins to tug at the structure of spacetime with surprising force. Before we settle into that, I would love to know where in the world you are listening from tonight and what sort of hour it is in your corner of things. Is it late evening with the room gone still around you, or one of those soft early hours when the mind is ready to wander a little farther than usual? There is something fitting, I think, about asking a question like that before a discussion of the Planck mass. Physics often sounds as though it is about remote and impersonal facts, but in practice it always begins with where we are, what we can observe, and how we choose to frame the mystery in front of us. Even the grandest theory starts with someone somewhere, looking carefully at the world and asking why it refuses to behave as neatly as expected. And if you find this gentle excursion soothing, intriguing, or simply a pleasant way to let the day loosen its grip a little, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this quiet corner of science drift toward other listeners who might enjoy a calmer way of thinking about the universe, especially when the universe is being particularly unreasonable. Now, the phrase Planck mass contains a small trap. It sounds as though we're about to discuss an object, some tiny thing with a measurable weight, perhaps a grain of matter hidden in the foundations of nature. But that is not quite right. The Planck mass is not a little pebble tucked behind reality. It is a scale, a threshold, a kind of signpost. It tells physicists that if you try to probe nature at energies associated with that mass, the ordinary separation between gravity and quantum physics stops working. The neat division breaks down. The rules that serve us so well in most situations begin to crowd each other, and when that happens, our best existing theories are no longer enough on their own. That may sound dramatic, and in fairness, physicists are not always opposed to a bit of drama when discussing the fate of fundamental theory. But this really is one of those places where the confidence of modern science becomes noticeably more cautious. We have two towering achievements in physics. On one side, there is general relativity, Einstein's description of gravity, space-time, curvature, and the grand architecture of the cosmos. On the other, there is quantum theory, which governs atoms, particles, fields, and the jittering uncertainty of the microscopic world. Each is spectacularly successful in its own domain. Each predicts reality with astonishing precision when used under the right conditions, and yet bring them too close together, and they begin to resist one another like two brilliant musicians trying to perform in different keys at the same time. That meeting point, or at least one of its clearest markers, is the Planck mass. To appreciate why this is so peculiar, it helps to remember that gravity is usually the quietest force in the microscopic world. Gravity governs planets, stars, galaxies, and the slow, reliable fall of objects toward the floor. It gives shape to the heavens and keeps your feet from drifting toward the ceiling. But if you look at individual particles, gravity seems almost embarrassingly feeble. A small magnet can lift a paperclip against the pull of the entire Earth, rub a balloon on your jumper, and static electricity begins performing party tricks that gravity cannot compete with. In particle physics, gravity is the relative no one quite knows where to seat at the wedding. It belongs to the family, certainly, but it does not seem especially influential once you enter the tiny crowded world of quarks and electrons. Quantum physics, by contrast, dominates that realm. It describes probability, fluctuation, uncertainty, and interactions so subtle and strange that they still feel faintly impossible even after a century of confirmation. It is the physics of the very small, but not merely small in size. It is small in action, small in scale, small in the granularity of nature's behaviour. It tells us that the microscopic world does not obey our ordinary intuition. Things do not possess crisp properties in the comfortable way teacups and chairs do. Instead, they blur, spread, fluctuate, and resolve only when pushed into definite outcomes. For most practical purposes, the two domains keep out of each other's way. If you are calculating the orbit of a planet, quantum uncertainty is not especially troublesome. If you are calculating the structure of an atom, gravity is so weak it can almost be left out with a guilty shrug. This separation is one of the reasons modern physics works as well as it does. Different tools for different scales, different descriptions for different circumstances, a very tidy arrangement, and like many tidy arrangements in science, one that begins to wobble the moment you ask a sufficiently awkward question. What if matter is compressed into an extremely small region? What if energy becomes enormous? What if space-time itself is examined so closely that the smooth stage of relativity is no longer smooth at all? What if the geometry of the universe has to obey quantum uncertainty, just like everything else? At that point, gravity cannot remain politely classical while the rest of physics goes quantum around it. It must join the trouble, and that is where the Planck mass steps into view. The name comes from Max Planck, one of the great founders of quantum theory, though the idea that now bears his name reaches beyond his original work. Planck realized that by combining certain fundamental constants of nature, one could define natural units, scales that do not depend on local habits, historical conventions, or how many thumbs happen to fit into a foot. These scales are woven into the universe itself. Among them are the Planck length, the Planck time, and the Planck mass. Each points toward a boundary where our current descriptions become strained. What makes the Planck mass especially odd is that it is tiny by ordinary standards and yet surprisingly large by particle standards. That contrast is part of what gives it its power. In the human world, it is not an enormous mass at all. You would not need a forklift or a team of heroic weightlifters to deal with it. But in the world of elementary particles, it is colossal, immense, vastly beyond the masses of the particles we routinely study. So the Planck mass occupies a strange middle ground. It is not large enough to impress a loaf of bread, but it is so large compared with known particle masses that it signals a domain very far beyond everyday quantum physics. This is where things begin to feel deliciously inconvenient. You might expect the scale where quantum gravity becomes important to be associated with something absurdly tiny in every sense, and in some ways it is. The corresponding length scale is fantastically small. The corresponding time scale is fantastically brief. But the mass scale is, from a human perspective, oddly substantial. That mismatch hints at something deep. It suggests that gravity, though weak at familiar particle energies, is tied to an enormous scale. To make gravity compete with quantum effects in a direct way, you must drive the system to extremes that our current experiments cannot remotely reach. So when physicists speak about the Planck mass, they are not merely naming a curious number. They are pointing to the energy range where the smooth geometry of space-time may begin to break into something more restless. They are gesturing toward the place where a particle can no longer be treated as a simple quantum object moving on a passive background, because the background itself may fluctuate. Space-time may no longer behave like a calm stage under bright theatre lights. It may become part of the cast, improvising unexpectedly and refusing to stand still for the scene. One of the challenges here is that our language was built in calmer regions of experience. We speak of particles as though they are tiny marbles, fields as though they are invisible fluids, and space-time as though it is a kind of cosmic fabric. These analogies are useful, but only up to a point. At the Planck scale, those pictures begin to fray. A particle compressed too tightly may invite gravitational collapse. A region probed too precisely may become so energetic that the act of measurement changes the geometry one hoped merely to inspect. This is one reason the Planck mass matters conceptually. It warns us that the old dream of observing reality ever more finely, as though it were simply waiting to reveal smaller gears and screws, may not survive indefinitely. There may be a point where closer inspection does not produce clearer detail, but instead disturbs the very structure of the stage. That is a rather humbling thought. Physics is often advanced by looking deeper, measuring better, slicing more finely, accelerating more energetically. We build larger machines, sharper detectors, more delicate clocks, and nature, generous thing that it is, often rewards the effort with new layers of order. Yet the Planck mass suggests that there is a regime where our usual strategies run into conceptual fog, not because the universe is being mischievous, though one might be forgiven for suspecting it from time to time, but because the categories we rely on may no longer be fundamental there. If that sounds like bad news, it is worth remembering that physics tends to become most interesting precisely when its comfortable assumptions fail. The cracks in an old theory are not signs of defeat. They are invitations. Classical mechanics could not explain blackbody radiation, and so quantum theory began to emerge. Newtonian gravity could not accommodate the deeper structure of spacetime, and so relativity arrived. Likewise, the tension around the Planck mass is not simply a problem to be tidied away. It is a sign that some deeper framework is waiting to be found, whether through string theory, loop quantum gravity, causal sets, asymptotic safety, or perhaps something not yet imagined by anyone with sufficient coffee and patience. There is also a philosophical side to this that I find difficult to resist. The Planck mass sits at a point where our divisions between large and small begin to fail in an interesting way. Gravity is the physics of the large, or so we often say. Quantum theory is the physics of the small, but the Planck mass reminds us that the universe does not actually respect our filing system. These are not separate provinces with a tidy fence between them. They are overlapping descriptions of one reality. The distinction is ours, born of convenience and scale. At most energies, that division works beautifully. At the Planck scale, the universe hands the folders back and says, very gently but very firmly, that this will not do. And so tonight, as we begin this subject, we are not rushing toward a final definition to pin neatly to the page. We are approaching a meeting place, a collision point, a scale at which the habits of modern physics begin to tangle. We will talk about why gravity is so weak compared with the other forces, why the Planck mass is both tiny and enormous depending on your point of view, why black holes lurk in the background of this discussion, and why some physicists suspect that spacetime itself may not be fundamental in the way we usually imagine. We will take our time with it, because this is one of those topics that punishes haste and rewards slow, careful curiosity. For now, it is enough to picture the Planck mass as a warning marker at the edge of our present understanding. Not a cliff exactly, and not a door either, though it has a bit of both about it. More like the moment in a long walk when the paved path runs out and the ground ahead becomes rougher, less mapped, more interesting. Up to that point, our theories have been reliable companions. Beyond it, they still whisper useful hints, but not with the same confidence. The map remains in your hand, though the symbols have started to look less reassuring. That may be why the idea lingers in the mind once you meet it. It is not merely a fact to memorize. It is a reminder that physics is unfinished. We have not reached the end of explanation. We are still surrounded by mysteries serious enough to keep theorists awake at odd hours, and experimentalists dreaming of machines large enough to make accountants faint. The Planck mass stands among those mysteries like a quiet but stubborn landmark. It says that somewhere far beyond familiar particle energies, gravity and quantum theory stop taking turns and speak at once. And perhaps that is the most exciting part. The Planck mass is not famous because it answers the deepest question. It is famous because it sharpens the question. It tells us where our current understanding becomes incomplete. It gives us a scale at which the universe is expected to reveal a more unified story, if only we can learn how to ask properly. That is a profound service from a single idea. Not all great concepts in physics give you a finished portrait. Some simply point, with admirable precision, toward the place where the portrait must eventually be painted. So as we move forward, we are carrying a quiet puzzle with us. Why should gravity become strong only at such an extreme scale? Why does the microscopic world tolerate such a weak gravitational influence at ordinary energies? What really happens when the Planck mass is approached? Does spacetime foam and flicker? Do black holes form in miniature? Do particles stop being the right language entirely? At the moment, the honest answer is that we do not know, and there is something refreshing about that. Physics is often introduced as the catalogue of what humanity has already figured out. It is also, very much, the art of learning exactly where our confidence ought to end. In that spirit, we can leave the evening here not with a conclusion, but with a clearer sense of the terrain. We have met the central character. We know that the Planck mass marks a scale where quantum physics and gravity can no longer be kept in separate rooms. We know that it belongs to a family of natural units tied to the deep structure of reality, and we know that it points beyond our present theories towards something more complete, though what form that completion might take is still uncertain. From here, the next step is to understand why this strange quantity was introduced at all, and how physicists learned to think in terms of natural scales rather than ordinary human ones. Because before the Planck mass became a signpost for quantum gravity, it emerged from a broader effort to ask a very basic question, in a very serious way. If the universe has its own built-in units, what are they trying to tell us? If the Planck mass seems puzzling at first, that is not because you are missing something obvious. It is puzzling because it sits in one of the least intuitive corners of the modern physics, where the language we use every day starts to work against us. The phrase itself sounds simple enough. Mass is familiar. We weigh fruit, estimate luggage, complain about parcels, and occasionally pretend not to notice how much a bookshelf probably weighs before trying to move it alone, and regretting every life choice that led to that moment. But the Planck mass is not familiar mass dressed in more formal clothing. It belongs to a completely different setting, and the setting matters. To get a feel for it, it helps to picture physics not as one smooth story, but as a series of stages of different sizes. On one stage live the objects of ordinary life. Apples fall, kettles boil, trains run late, and gravity behaves in the calm, dependable way we have come to expect from it. On another stage live atoms and particles, a much smaller world where quantum rules dominate and certainty begins to loosen. Things are no longer simply here or there in the crisp, everyday sense. They smear into possibilities, fluctuate, interfere, and surprise us with a consistency that somehow makes the surprises scientific. Usually these stages do not interfere too much with one another. We can talk about a falling stone without worrying about quantum uncertainty in any practical sense. And we can talk about an electron without worrying very much about the gravitational pull it exerts on anything nearby. The worlds overlap in principle, of course, but in practice each scale has its own leading actor. In the world of planets and stars, gravity dominates the script. In the world of particles, gravity barely gets a speaking part. That is part of why the Planck mass is so strange. It points to a stage that is unimaginably small, and yet somehow demands an actor that is, by particle standards, absurdly heavy. That combination is the heart of the oddity, the smallest stage with the heaviest actor, a realm so tiny that space and time themselves may stop behaving smoothly, and yet the relevant mass scale is enormous when compared with the particles we know. If you only hear one thing tonight, let it be that. The Planck mass is not weird because it is merely large or merely small. It is weird because it combines those ideas in a way our intuitions do not like. When physicists say something is heavy in particle physics, they are not usually thinking in the same way you do when lifting a suitcase. They mean that the mass associated with a particle is large compared with the masses of familiar fundamental particles. An electron is light. A proton is much heavier than an electron, though still tiny in ordinary terms. Even the heaviest particles discovered in high-energy physics are still nowhere near the Planck mass. So when this scale appears, it towers over the rest of the quantum cast like a theatre actor who has wandered into the wrong production and accidentally blocked the entire stage. And yet, from the perspective of everyday life, the Planck mass is not huge at all. That is what makes people blink the first time they encounter it. In grams, it is tiny. You would not notice it on a kitchen counter unless someone pointed it out. It would not flatten the table or force a dramatic evacuation of the room. And still, in the microscopic world, it is giant. That mismatch is not a cute numerical accident. It is telling us something essential about the relative weakness of gravity and the scales at which it becomes impossible to ignore. We're used to gravity feeling strong because Earth is enormous. Stand up and gravity is there. Trip over and gravity is there with perhaps more enthusiasm than you wanted. Drop a spoon and it heads for the floor rather than floating off into philosophical uncertainty. But the strength of gravity in daily life comes from accumulated mass, from planets and stars and vast collections of matter working together. At the level of individual particles, gravity is astonishingly feeble. Other forces completely overshadow it. That is why physicists can spend entire careers studying particle interactions without ever having to worry seriously about gravity in the calculations. It is present in principle, but irrelevant in practice. So how do we get from that quiet weakness to a mass scale so large that it seems to sit above the rest of particle physics, like a mountain above garden furniture? The answer is that the Planck mass measures the point where gravity would finally become as important as the other ingredients in a quantum process. It marks the energy scale where the gravitational interaction is no longer a trivial background whisper. At that point, gravity ceases to be ignorable. It joins the argument properly. There is a useful way to think about this without dragging us into formulas. Imagine trying to investigate smaller and smaller distances. To do that, you generally need higher and higher energies. This is one of the recurring themes of modern physics. If you want to see smaller structure, you need probes with shorter wavelengths and therefore greater energy. That is why particle accelerators are large, expensive, and forever being described as either triumphs of human ingenuity or excellent reasons to worry about the budget. The deeper you want to look, the more violently you have to poke reality. Now, as you keep increasing that energy, two things happen. First, quantum behavior remains important because you are still dealing with microscopic scales. Second, gravity, which was negligible at lower energies, becomes more relevant because energy itself gravitates. In Einstein's view, gravity responds not just to rest mass in the ordinary sense, but to energy and momentum more broadly. So as you pack more energy into a smaller region to inspect nature more closely, you are not merely illuminating the target, you're also adding gravitational influence to the situation. Push this far enough, and you reach a genuinely uncomfortable possibility. The act of probing a tiny region may itself disturb space-time so strongly that the very notion of a smooth background breaks down. In looser language, your measuring device starts stomping through the flower bed rather than peering delicately at the petals. At such scales, the old assumption that particles move through a passive geometric stage may stop making sense. The stage itself responds, fluctuates, and may even cease to resemble a stage at all. That is the conceptual territory signposted by the Planck mass. It tells you when your probe becomes heavy enough, in the particle sense, that gravity can no longer be treated as an afterthought. It is the threshold at which the geometry of space-time enters the microscopic drama directly. In most of particle physics, this does not happen. You can treat space-time as a fixed arena. The fields do their quantum business on top of it. But near the Planck scale, that comfortable arrangement begins to fail. This is why the phrase smallest stage with the heaviest actor works so well. the stage is tiny beyond ordinary comprehension. The actor, compared with everyone else in particle physics, is enormous. And crucially, the actor is so imposing that it begins to deform the stage just by being there. That is not how theatre is usually supposed to work. It is rather like hiring a dancer for a delicate performance, only to discover that every step cracks the floorboards and bends the lighting rig. At that point, one cannot continue with the original choreography. Another part of the strangeness comes from the way we usually divide physics into categories. We like the large and the small to stay in their lanes, cosmic physics over here, atomic physics over there. But the Planck mass represents a point where small scale does not mean weak gravity. That is deeply counterintuitive because in ordinary experience, gravity becomes more significant as masses grow large and distances become astronomical. Here, however, the relevant region is minuscule, yet the energy concentration is so extreme that gravity pushes back with real force. The very small becomes, in gravitational terms, serious. It also helps explain why quantum gravity is so difficult to test directly. The Planck mass is colossal compared with the energies of the particles we can produce in laboratories. Our best accelerators are extraordinary machines, but they are nowhere near this threshold. We can infer much. We can reason, model, and speculate with increasing sophistication. But we cannot simply dial up the Planck scale in a machine and see what falls out, not with present technology. Nature has placed the crucial junction annoyingly far beyond easy reach. It is one of the universe's less considerate habits. Still, the significance of the Planck mass does not depend on our ability to build a machine that reaches it tomorrow afternoon. Its importance lies in what it teaches us about the architecture of theory. If there is a scale where gravity and quantum mechanics collide, then any complete description of reality must account for that collision. General relativity alone will not do, because it treats spacetime classically. Quantum field theory alone will not do, because it relies on that classical spacetime as a stable background. Each theory works beautifully within its own range, but the Planck mass tells us there is a range where neither can claim full authority. That is why it is often described as a natural scale. Not a human convenience, not a historical accident, not a number born of our choice to count in one system rather than another. It emerges from the basic constants that govern gravity, quantum behavior, and relativity. In that sense, it belongs to the universe itself. If you hand the same laws of physics to any sufficiently capable civilization anywhere in the cosmos, they will discover the same Planck mass. They may call it something much more elegant or possibly much less, depending on their academic culture, but they will find it. And once found, it raises an almost teasing question. Why are the particles we know so much lighter than this scale? Why is there such an enormous gap between the masses familiar from particle physics and the Planck mass? This is one form of what people sometimes call the hierarchy problem. Though that phrase has its own technical uses and complications, the basic unease is easy enough to state. If the Planck mass is the natural scale where gravity becomes fully entangled with quantum physics, why is so much of the known particle world sitting so far below it? Why is there such a dramatic separation between the scale of gravity's full quantum importance and the scales of the standard model? Questions like that have driven whole branches of theoretical physics. Some have hoped that supersymmetry might help explain the gap. Others have explored extra dimensions, composite models, or new symmetry principles. Some propose that the apparent hierarchy is not a problem in need of repair, but a fact that may one day find an explanation through cosmology or deeper structure. As ever in fundamental physics, every answer breeds fresh questions, and every fresh question somehow acquires a conference series and a collection of very serious slides. There's also a deeper lesson in the fact that the Planck mass is so large for a quantum scale. It reminds us that gravity is unlike the other interactions. The electromagnetic, weak and strong interactions fit naturally into the framework of quantum field theory, as we currently understand it. Gravity resists that treatment. It can be approximated quantum mechanically in limited settings, and one can calculate certain effects, but the straightforward methods that succeed elsewhere do not carry us cleanly all the way. In that sense, gravity is not merely another force waiting patiently for its turn in the formal machinery. It is the one interaction that keeps hinting that the machinery itself may need rebuilding. That possibility becomes particularly vivid when one thinks about the Planck length alongside the Planck mass. The mass tells us the energy scale where trouble begins. The length tells us the distance scale, where spacetime may stop being smooth. Together they suggest a world in which the geometry we take for granted may dissolve into something more granular, more relational, or more abstract than distance and duration, as ordinarily conceived. Perhaps spacetime is emergent. Perhaps geometry comes from information, entanglement, or some deeper combinational structure. Perhaps the smooth continuum is no more fundamental than the flowing surface of water is fundamental to molecules. If so, the Planck mass is like a warning label attached to the smooth picture. Fine for ordinary use, it says, not guaranteed at extreme scales. At this point, it is worth acknowledging a temptation that often appears in discussions like these. One wants to imagine the Planck scale as the final basement level of reality, the last tile in the floor, the smallest meaningful chunk of existence. Perhaps it is. But physics has taught us to be cautious with such declarations. Every time we become too confident that we have reached the deepest level, the universe produces another hatch, another hidden corridor, another level beneath the cellar. The Planck mass marks a place where current theory struggles, but it does not automatically reveal what lies beyond. It tells us where our understanding becomes incomplete, not what the final replacement must be. And yet, even without a completed theory of quantum gravity, the Planck mass already serves as a remarkably clear conceptual guide. It tells us that the microscopic world is not merely a scaled-down copy of the ordinary world. Shrink enough, and you do not simply find smaller objects obeying the same assumptions. You find thresholds where the assumptions themselves fail. At one threshold, quantum behavior becomes unavoidable. At another, relativity reshapes our notion of space and time. At the Planck threshold, those revolutions meet and begin arguing over who gets to define the furniture. That image may sound playful, but the underlying point is severe. The Planck mass is where the foundational concepts of modern physics start to overlap in a way we do not yet know how to describe coherently. It is the heavy actor, not because it is physically cumbersome in an everyday sense, but because it carries the weight of unresolved theory. It walks onto the smallest stage and suddenly everything we thought we knew about the stage directions becomes uncertain. So when we continue from here, it will be useful to keep two impressions in mind at once. First, the Planck mass is a natural marker of the scale where quantum physics and gravity become equally impossible to ignore. Second, it is strange precisely because this scale is attached to a world of extreme smallness yet corresponds to an enormous mass by the standards of particle physics. That tension is not a side note, it is the point. The small and the heavy meet here in a way that exposes the limits of our current map. From there, the natural thing to ask is how physicists came to identify such a scale in the first place. What was Max Planck actually doing when he introduced the broader family of natural units? Why should constants of nature be combined into scales that seem to exist independently of human convention? And what does it mean to say that mass, length and time can be built from the structure of the laws themselves rather than from the convenience of kings, merchants, or people trying to standardize cloth measurements several centuries ago? That turn, from arbitrary units to natural ones, is where the story becomes even more interesting, because it reveals that the Planck mass is not an isolated curiosity. It is part of a deeper attempt to let nature set the terms of the conversation. Long before the Planck mass became a signpost for this place where gravity and quantum theory begin to collide, there was simply Max Planck, a careful, deeply serious physicist trying to solve a problem that looked at first almost technical. It did not arrive with thunder. It did not announce itself as the beginning of a revolution. It was not introduced to the world with dramatic music and a curtain pulled back from the ruins of classical certainty. It began, as many scientific upheavals do, with a stubborn mismatch between theory and experiment, a small embarrassment, the sort of thing a confident scientific age expects to tidy away with a little more work and perhaps a better blackboard. That age, in the late 19th century, had every reason to feel confident. Classical physics had become one of the great triumphs of human thought. Newtonian mechanics described motion with extraordinary power. Maxwell's theory of electromagnetism had unified electricity, magnetism, and light into a single, elegant framework. Thermodynamics had brought order to heat, work, and energy. Across Europe, there was a growing sense that the foundations of physical reality were more or less understood. Yes, there were details to improve, constants to measure more precisely, and certain awkward corners still to smooth over, but the main architecture appeared secure. The house of classical physics stood tall, beautifully designed, and impressively furnished. It is often said, perhaps a little too neatly, that some physicists at the time believed there was almost nothing important left to discover. History tends to simplify these moods into tidy slogans. Real scientists are usually more cautious and less dramatically foolish than later generations enjoy pretending. Even so, there really was a widespread sense that physics had reached maturity. The remaining work looked like refinement, not overhaul. It was as though the great map of nature had been drawn, and only the smaller roads remained to be inked in. Then came the cracks. One of those cracks opened around the study of heat radiation, specifically the light emitted by a hot object. That may sound oddly domestic for the start of a conceptual earthquake. One imagines a stove, a glowing piece of metal, the orange warmth of a heating element, something rather ordinary and faintly useful. But this simple glow concealed a deep problem. Physicists wanted to understand how much radiation a heated object emits at different colours or frequencies. If you heat something gently, it glows dull red. Heat it further, and the glow shifts toward brighter colours. There is structure here, regularity, a pattern in the way matter radiates energy. And physicists, being who they are, naturally wanted the pattern expressed cleanly and exactly. The idealized object for this problem was the black body, a perfect absorber and emitter of radiation. It does not reflect light. It does not favor one color over another for sentimental reasons. It provides a clean theoretical case, a kind of perfect testbed for understanding thermal radiation. Experimentalists had gathered increasingly good data on how black bodies radiate. The curve was known. The challenge was to derive that curve from theory. Classical physics, with its formidable reputation, seemed more than capable of handling the matter. After all, between mechanics, electromagnetism, and thermodynamics, what could possibly go wrong? Quite a lot, as it turned out. The existing classical approaches gave answers that worked only in limited ranges. Some formulas matched the low-frequency part of the spectrum fairly well. Others did a better job at high frequency in certain circumstances. But no classical derivation could reproduce the full observed curve properly. Worse still, when physicists applied the standard classical assumptions too straightforwardly, they obtained a catastrophic prediction. At high frequencies, the emitted energy would rise without bound. According to the theory, a hot object should pour out an absurd and effectively infinite amount of ultraviolet radiation. It should become an impossible furnace of energy. Nature, with admirable calm, declined to do any such thing. This disaster later acquired a famously dramatic name, the ultraviolet catastrophe. It deserves that title, though like many catastrophes in science, it was less a loud explosion than a deeply embarrassing failure of a trusted framework. The equations had marched confidently off a cliff, and experiments remained on solid ground watching them fall. That discrepancy mattered because it suggested the problem was not a minor technical slip. Something in the assumptions themselves had gone wrong. Enter Max Planck, not as a flamboyant destroyer of old doctrines, but as a meticulous conservative thinker who did not set out to overthrow classical physics at all. This is one of the pleasing ironies of scientific history. Revolutions are not always launched by people waving manifestos. Sometimes they begin with someone trying very hard to preserve order. Planck was not, by temperament, a wild conceptual gambler. He respected established theory deeply. He believed in the power of continuity, rationality, and careful derivation. He was in many ways exactly the sort of physicist one would expect to repair a damaged system rather than replace it. Planck had already made a name for himself through work on thermodynamics and radiation theory. He was drawn to general principles and mathematical precision. The black body problem appealed to him because it sat at the meeting point of heat, light, and equilibrium, all areas where the 19th century had built impressive tools. He hoped, not unreasonably, that the right theoretical treatment would restore agreement between calculation and observation. What happened instead is that he found himself driven toward an assumption he did not initially regard as a declaration of new physics. It was more like a desperate but ingenious patch, a mathematical move introduced to make the results come out right. And here one must be careful, because scientific stories are often retold in a way that makes great discoveries sound instant and theatrical. There was no single moment in which Planck leapt onto a chair and cried out that energy is quantized and reality has changed forever. It was slower, more awkward, more reluctant. He was trying to fit the data. He introduced an unfamiliar idea because the usual ideas would not work. The key move was this. Planck proposed that the oscillators responsible for emitting radiation in the walls of the blackbody cavity could not exchange energy in perfectly continuous amounts. Instead, the energy came in discrete packets. Not arbitrary packets, but packets proportional to the frequency of the oscillation. Higher frequency meant larger packets. Lower frequency meant smaller ones. This tiny conceptual shift, if one can call a revolution tiny, allowed him to derive the observed radiation curve correctly. Suddenly the catastrophe disappeared. The spectrum behaved. Theory and experiment shook hands again, though perhaps with some lingering suspicion. At first, Planck did not fully present this as a claim about the deeper structure of reality. He viewed it in a somewhat formal way, a feature of the oscillators and their interaction with radiation, perhaps even a mathematical trick of restricted applicability. But the idea had escaped into the world, and it was not going back into its box. Energy, at least in some contexts, was not behaving as a smooth, infinitely divisible fluid. It came in chunks. Small chunks, yes, but definite ones. Nature, at a fundamental level, had shown a preference for granularity. That was the crack. Not yet the complete collapse of classical certainty, but the first undeniable fracture. Because classical physics had assumed continuity very deeply. The world it described was smooth in both concept and mathematics. Positions, velocities, energies, fields, all varied continuously. One could imagine dividing quantities further and further without limit. That intuition had served physics magnificently well. But Planck's results suggested that the world might resist such smoothness when examined in the right way. The scale of the chunks was tiny, far below daily notice, yet their conceptual significance was enormous. It is difficult to overstate how unsettling this was. Not because the idea was emotionally dramatic in itself, but because it touched the underlying style of physical thought. Classical theory had taught generations of physicists to picture the world as a grand, continuous mechanism. Quantum discontinuity was not merely a new term in an equation, it was a challenge to the texture of reality. It implied that some quantities change in steps, not flows. That the microscopic world is not just a smaller version of the macroscopic one. That the deeper you look, the less your comfortable intuitions may survive intact. Planck introduced the constant that now bears his name as part of this work, a new fundamental quantity setting the scale of the discrete action involved. At the time, it was simply a number needed to fit the blackbody curve, but it soon became clear that this constant was far more than a patching parameter. It was a marker of an entirely new regime of physics. Whenever it appears significantly in a problem, classical reasoning begins to wobble, and quantum behaviour becomes essential. In that sense, Planck had not merely solved a radiation puzzle. He had uncovered a new basic feature of the universe. He did not do it alone, of course, at least not in the historical sense of what came next. Scientific ideas, once released, develop through many minds. Einstein took Planck's quantum hint far more boldly than Planck himself initially did. In explaining the photoelectric effect, Einstein argued that light itself behaves in discrete quanta, not just the oscillators in matter. That was an even more radical step. Then came Bohr, Heisenberg, Schrödinger, de Broglie, Dirac, and others, each contributing to the growing quantum framework. But the first opening in classical reality, the first unavoidable sign that the old assumptions were incomplete, came with Planck's radiation law. There is something rather human in the way this happened. Physics did not move forward because scientists wanted mystery for its own sake. They moved because nature would not cooperate with the old script. The equations failed. The measurements disagreed. The world, rather politely but quite firmly, refused to be described in the old way. That is often how genuine progress begins. Not with the thrill of novelty, but with the stubborn refusal of reality to flatter our expectations. And the black body problem itself is a lovely example of how profound ideas can emerge from what seems like a narrow technical issue. No one looking casually at the warm glow of heated metal would guess that it contains the seeds of quantum theory, yet it does. A furnace, a cavity, a radiation curve, and suddenly the continuity of classical physics begins to crack. It is one of the many reminders that the universe likes to hide its biggest revelations inside ordinary phenomena. One may spend years thinking one is studying thermal equilibrium and wake up to find one has destabilized the foundations of physics. Planck's personal relationship to the revolution he helped start was, by all accounts, complicated. He accepted the necessity of the new constant and the success of the theory it enabled, but he did not initially embrace every radical interpretation that later developed around quantum mechanics. That is understandable. To discover a crack in an old building does not automatically mean you enjoy watching the walls come down. Planck had been educated in the classical tradition. He admired its coherence. He had not set out to destroy it, only to repair one troublesome section. Instead, he discovered that the structure itself required alteration. This is part of what makes his role so interesting in the larger story of the Planck mass and Planck units. The name Planck is attached today to scales that point toward the limits of our current understanding, scales where quantum physics and gravity begin to demand reconciliation. But the origin of that naming lies in an earlier confrontation with the limits of classical thought. Planck's first great contribution was not to quantum gravity, which did not yet exist as a field, but to the realization that nature contains a built-in scale of action that classical continuity cannot absorb. Once that scale enters the scene, a new kind of physics becomes necessary. In retrospect, one can see why this mattered far beyond blackbody radiation. If there is a fundamental constant setting the scale of quantum effects, then one can combine it with other constants of nature to construct units that are not arbitrary human inventions. One can build natural units of length, time, mass, and so forth. This was one of Planck's own remarkable insights. He understood that with certain universal constants in hand, physics could define scales belonging to nature itself rather than to local custom. No more dependence on feet, pounds, or the historical whims of kings and merchants. Instead, one could ask what scales are woven into the laws of reality. That move was conceptually powerful because it reframed the question of measurement. Human units are convenient and often deeply silly in historical origin. Natural units are different. They reveal the structure of the laws. They tell us where certain combinations of physical principles become equally important. And from that perspective, the Planck mass becomes much more than a unit. It becomes a signpost erected from the constants themselves, pointing toward the domain where gravity, relativity and quantum action all intersect. But one must not rush there too quickly, because the emotional and intellectual significance of Planck's original breakthrough deserves a little more attention. The first crack in classical reality was not simply the discovery that something is discrete. It was the discovery that the most successful physical framework ever built up to that time had a limit that could not be fixed from within. That is always an unsettling moment in science. We're used to theories succeeding. We become attached to them. They train our intuition. They shape what feels sensible. Then one day a phenomenon appears that the theory cannot digest, and we face a choice. Do we force the world into the theory, or do we enlarge the theory to fit the world? Planck, almost despite himself, chose enlargement. He gave the world a constant that was initially small in numerical value and enormous in consequence. He showed that a careful fit to experiment can reveal not merely a better approximation, but a new layer of reality. And he opened the door to a century of physics in which certainty would become more subtle, measurement more delicate, and the basic ingredients of nature more elusive than classical imagination had ever guessed. There is another reason this matters for the story we are building. The Planck mass can sound, at first hearing, like a strange late addition to physics, something belonging only to advanced theories and speculative frontiers. In fact, it is connected by lineage to one of the earliest and most profound shifts in modern science. It carries the name of the man who first found the scale at which classical continuity gives way to quantum grain. That historical connection is not decorative. It matters because the Planck mass belongs to a broader family of thresholds, each one rooted in the recognition that our ordinary categories fail under enough pressure. Classical reality did not collapse all at once, it cracked. Then the cracks widened. Planck opened one, Einstein widened another. Quantum mechanics and relativity pulled the old structure in different directions until it was impossible to pretend that the 19th century picture could remain untouched. By the middle of the 20th century, physics had become something both richer and stranger than its earlier practitioners could have comfortably imagined. And still the work was not done, because the new frameworks, brilliant as they were, did not fit together completely. Quantum theory and gravity remained uneasy neighbours. The crack in classical reality had been the beginning, not the end. That is worth holding in mind. Planck's contribution was foundational, but it was also incomplete by design. He found the constant. He introduced the discontinuity. He made it possible to think in natural units. But he did not deliver the final synthesis of quantum theory and gravitation. No one has, at least not in a form accepted and confirmed by the wider field. So when we speak of Planck scales now, we are standing at the far end of a story that begins with the glow of heated matter and the first failure of classical continuity. It is a rather elegant progression when you step back from it. A problem in thermal radiation reveals a fundamental quantum of action. That quantum constant becomes one of the pillars from which natural units are built. Those natural units define scales where the smooth picture of spacetime may break down, and among them sits the Planck mass, quietly indicating the point where gravity can no longer remain outside the quantum conversation. The same name joins the first cracks in classical reality to the frontier where our current reality theories still refuse full reconciliation. So before we move into the meaning of mass itself and what physicists are really talking about when they compare scales like these, it is worth pausing with Max Planck a little longer in spirit, if not in biography. A conservative thinker solving a practical theoretical problem introduces an odd assumption to save agreement with experiment. He does not yet know he has opened a new era. The old world of continuous certainty remains standing for the moment, but a fracture has appeared in the wall. Through it, faintly at first, comes the light of a stranger universe, and once that light appears, physics can no longer go back to sleep. The next thing it must ask is what exactly mass means inside this new world, because if the Planck mass is to tell us something deep about the collision of gravity and quantum theory, then we need to be much more careful than everyday language allows. Mass in physics is not simply heaviness in the kitchen scale sense. It is tangled up with inertia, energy, interaction, and the structure of theory itself. That is where the path leads next, and it matters, because one cannot appreciate why the Planck mass is so extraordinary until one understands what physicists mean when they speak of mass at all. By the time most of us first hear the word mass, it has already been bundled up with a very simple everyday feeling. Mass is how much stuff something has. Mass is why a pebble is easy to lift and a wardrobe is not. Mass is why a shopping bag can go from pleasantly manageable to deeply offensive over the course of one ambitious trip to the grocer. It seems straightforward, almost too straightforward to deserve much philosophical attention, and in ordinary life that simplicity serves us well enough. We can move furniture, weigh ingredients, compare objects, and get on with our day without worrying too much about the deeper meaning hiding inside the word. But physics has an irritatingly charming habit of taking familiar terms and revealing that they contain far more than we thought. Time turns out not to be merely time. Energy turns out not to be merely oomph. Space turns out not to be an empty container waiting politely for things to happen inside it. And mass, once you begin looking closely, turns out to be a concept with several layers, each important, each slightly different, and all of them relevant when we eventually return to the Planck mass. If we're going to understand why that scale matters, we need to slow down and ask what physicists really mean when they speak of mass at all. The first layer is the one closest to ordinary intuition. Mass measures inertia. That is to say, it measures how stubborn an object is when you try to change its state of motion. A light object speeds up easily when pushed. A heavy one resists. If you give the same shove to a tennis ball and to a grand piano, the tennis ball takes the hint immediately, while the piano behaves as though your effort is touching but insufficient. In this sense, mass is not simply a quantity of material in some vague philosophical sense. It is resistance to acceleration. It is the reluctance of matter to have its motion altered. This is such a useful idea that it became central to classical mechanics. In Newton's framework, mass appears as the measure of how much an object resists change in motion. The larger the mass, the more force you must apply to achieve the same acceleration. That is a wonderfully clean piece of reasoning, and it works so reliably in daily life that we rarely stop to admire how profound it really is. The universe could have been much less cooperative. Objects might have responded to pushes in some maddeningly non-linear way depending on colour, mood, or whether anyone was in a hurry. Instead, mass gives order to motion. It makes dynamics calculable. It allows apples, cannonballs, bicycles, and badly thrown house keys to obey the same broad logic. There is, however, a second classical meaning of mass that quickly enters the story. Mass also measures how strongly an object responds to gravity. A more massive object has a stronger gravitational pull and also experiences gravity in a particular way. Here, things become immediately curious. The mass that measures inertia and the mass that measures gravitational behaviour turn out to be the same, at least as far as all experiment can tell. That fact is so familiar now that it is easy to miss how astonishing it is. Why should the quantity that tells you how much an object resists acceleration also be the quantity that determines its gravitational role? Those are conceptually different jobs. One concerns response to force in general. The other concerns participation in a specific interaction, gravity, and yet nature seems to use the same number for both. This quiet identity became one of the clues that eventually guided Einstein toward general relativity. If inertial mass and gravitational mass are fundamentally equivalent, perhaps gravity is not an ordinary force in the same way the others are. Perhaps it has something to do with the geometry of motion itself. That suspicion turned out to be enormously fruitful. But even before Einstein, the equality was already one of those facts that looks almost too elegant not to mean something deeper. Then relativity arrives and makes the old picture both richer and slightly harder to discuss at family dinners. In Einstein's world, mass is no longer entirely separable from energy. The famous relationship between the two is so well known that it has drifted into popular culture and now appears cheerfully on mugs, posters, and things sold in museum gift shops to people who would rather like to feel clever while making tea. But the deeper point often gets blurred. The relation between mass and energy does not mean mass is simply some exotic fuel waiting to explode dramatically if handled with sufficient enthusiasm. It means that mass is a form of energy, and energy contributes to the physical content of the world in a fundamental way. This matters because it changes how we think about what gravity responds to. In relativity, gravity is not merely a force between inert lumps. It is the response of space-time geometry to energy, momentum, pressure, stress, and the whole local bookkeeping of physical content. Rest mass remains important, but it is no longer the whole story. A box of light, for instance, contributes gravitationally because light carries energy and momentum even though it has no rest mass. Heated matter can weigh more than cooler matter because extra internal energy contributes. A compressed spring has slightly more mass than an uncompressed one because the stored energy counts. Physics, never shy about making simple words more complicated, tells us that mass cannot be understood in isolation from the broader concept of energy. At this point, one begins to see why the word mass becomes slippery in advanced contexts. When particle physicists talk about the mass of a particle, they often mean its invariant mass, the mass associated with the particle in its own rest frame, the quantity that remains the same regardless of how fast the observer is moving relative to it. That is a much sharper idea than merely saying how heavy something feels. Weight depends on gravity, mass does not, at least not in that ordinary sense. A hammer on the moon and a hammer on Earth weigh differently, but their mass is the same. Even this distinction, simple though it sounds, is vital, because the Planck mass is not about how heavy something would be on a scale in a laboratory. It is about a deep scale of energy and interaction, written into the laws of physics themselves. In everyday speech, we mix mass and weight all the time because daily life forgives the laziness. Physics does not. Weight is the force exerted by gravity on a mass in a given gravitational field. Mass is the more intrinsic property. Weight can vary with location. Mass stays with the object. If you carry a bag of groceries up a mountain, your legs may report that something has changed, but the mass of the groceries remains stubbornly itself. The difference is elementary in one sense and conceptually crucial in another. When we move toward the Planck mass, confusing mass with weight would be like confusing the script with the stage lighting. Both matter, but they are not the same thing. Now there is another development that makes the idea still richer. In modern particle physics, mass is tied to the behavior of fields. The standard model does not begin with little hard pellets of matter carrying mass as an obvious birthright. It begins with quantum fields, extended entities filling space, whose excitations appear to us as particles. In that language, a particle is not a tiny billiard ball with a label glued to it. It is a localized excitation of an underlying field. Mass then becomes part of the description of how that field behaves. It influences how the excitation propagates, how it responds to momentum, how much energy is associated with its presence even when it is at rest. This shift in picture is easy to say and harder to feel intuitively. We are much better at imagining marbles than fields. A marble sits there. A field seems to be everywhere and nowhere in exactly the wrong ratio for human comfort. Still, the field picture is the one that works, and in that picture, mass is not merely a substance count. It is part of the dynamical character of a field. It affects what kinds of particles can exist, how far forces reach, how interactions unfold, and what sorts of symmetries nature preserves or breaks. That last point becomes especially important with the Higgs mechanism, which is often introduced to the public in a way that sounds both dramatic and slightly overconfident. One sometimes hears that the Higgs field gives everything mass, full stop, as though the universe were a village fete, and the Higgs had been assigned to hand out mass from a folding table near the raffle. The truth is more specific and more interesting. Certain elementary particles acquire mass through their interaction with the Higgs field, whose non-zero background value changes the symmetry structure of the electroweak theory. This gives rise to masses for the weak bosons and for fermions through their couplings, though not all mass in the world comes directly from the Higgs in any simple everyday sense. Much of the mass of ordinary matter, for example, arises from the energy of strong interactions inside protons and neutrons, rather than from the bare masses of the constituent quarks alone. That is a wonderfully revealing fact. The mass of the stuff around you is not merely the sum of tiny pre-existing lumps. A great deal of it emerges from binding energy, motion, and the restless quantum dynamics inside hadrons. In other words, the mass of ordinary matter is deeply tied to energy again. This time not just in the abstract relativistic sense, but in the concrete internal life of the particles that make up atoms. Matter is not a passive pile of tiny bricks. It is an organized storm of fields and interactions, and mass is one way that structure announces itself. By now, the simple childhood notion of mass as amount of stuff has become noticeably less secure. Mass measures inertia. Mass participates in gravity. Mass is related to energy. Mass belongs to particles as invariant content. Mass arises in field theory through specific mechanisms and interactions. Mass can even emerge significantly from confined dynamical energy, rather than from elementary bare inputs alone. The concept is not falling apart exactly, but it is becoming much more alive than it looked on first acquaintance. And this is precisely why the Planck mass cannot be understood as just a very large or very small amount of stuff. It is not a tiny grain hidden at the centre of the atom. It is not the heaviest little object in nature waiting to be discovered under a sufficiently determined microscope. The Planck mass is a scale. It is built from fundamental constants in a way that tells us when quantum effects and gravitational effects become comparably important. To appreciate that, you have to be able to think of mass in the language of energy, dynamics, and theory, not merely in the language of heaviness. There is a useful comparison here with temperature. If someone asked what temperature really means, you could begin with the everyday answer: hot things are hot, cold things are cold. Tea left alone becomes disappointing, but physics goes deeper. Temperature is connected to the average behaviour of microscopic constituents, to energy distributions, to statistical descriptions of many particles. The everyday feeling is real, but it is not the full concept. Mass is similar. The ordinary idea gets you started. Physics takes it apart and rebuilds it in a more fundamental form. One reason this matters so much near the Planck scale is that energy concentration itself gravitates. When you try to localize a particle more tightly, quantum reasoning tells you that the associated momentum uncertainty grows. With higher momentum comes higher energy, and higher energy means stronger gravitational relevance. Suddenly, the old separate roles begin to blur. Mass as inertial content, mass as energetic content, and mass as source of gravitational influence all start pressing into the same tiny region. That is why the Planck mass appears as a natural boundary marker. It is the point where these different aspects can no longer be treated independently, with the comfortable approximations that work elsewhere. In lower energy particle physics, one can often ignore gravity altogether. In macroscopic gravity, one can often ignore quantum uncertainty. At the Planck scale, those luxuries vanish. Mass, in the deep physical sense, is no longer just a parameter attached to an object. It becomes part of a struggle between descriptions. Too much energy packed into too small a region, and space-time itself is no longer a passive background. The quantity we call mass becomes entangled with the possibility that geometry fluctuates, collapses, or demands a different language altogether. There is also something philosophically satisfying in how the concept evolves. Physics tends to punish nouns. We like nouns because they make the world feel stable. Matter, mass, space, time. They sound like things one could point to. But the deeper one goes, the more these nouns become relationships, structures, behaviours, and roles within theory. Mass is not merely an object attribute in the old solid sense. It is part of how physical reality is organised. It tells us how systems resist change, how they carry energy, how they source gravity, and how they appear in field equations. The closer we get to fundamental theory, the less mass looks like a simple chunk, and the more it looks like a node in a web of relations. That relational character is one reason the Planck mass is so revealing. Because it is defined from universal constants, it does not belong to one particular particle or object. It belongs to the architecture of the laws themselves. It tells us that if mass, understood as energy scale, reaches a certain value, then our usual separation between quantum theory and gravitation becomes untenable. That is not a fact about one object. It is a fact about the grammar of nature. If all of this feels slightly more abstract than weighing potatoes, that is because it is. But abstraction in physics is not the opposite of reality. It is often what reality requires when everyday language becomes too cramped. The challenge is to hold on to the physical meaning without retreating into pure vagueness. So perhaps the cleanest way to say it is this. In the language of physics, mass is a measure of inertial resistance, a form of energy, a source of gravitational influence, a feature of fields and particles, and sometimes an emergent consequence of interaction energy, rather than a primitive ingredient. It is not one simple thing. It is a family of closely related roles that line up beautifully in familiar settings and become more delicate in extreme ones. That delicacy is exactly what we need for the road ahead, because once we start constructing the Planck mass from nature's constants, we will no longer be dealing with mass in the domestic sense of how much one can carry before muttering darkly about stairs. We will be dealing with a natural energy scale, a threshold that tells us when spacetime and quantum behaviour begin to interfere with one another so strongly that our best separate theories stop being enough. To see why that scale is built the way it is, and why it says something so profound about the universe, we now have to turn from the meaning of mass to the deeper question of natural units themselves. Why should the universe possess scales that emerge from its own laws? And what exactly are those constants trying to tell us when they are combined in the right way? Once physicists began to suspect that the laws of nature themselves might contain their own built-in scales, the question became how to uncover them without smuggling in human habits by the back door. That may sound more philosophical than practical, but it is actually one of the cleanest and most revealing moves in theoretical physics. Most of the units we use in daily life are historical conveniences. A meter, a second, a kilogram. These are useful, stable, and carefully defined, but they are still part of a human bookkeeping system. They tell us how we have chosen to measure reality, not necessarily how reality would choose to measure itself. If one wants to know whether the universe has its own preferred scales written into the laws rather than imposed by custom, then one has to build them from constants that appear to be fundamental everywhere. This was one of Max Planck's great conceptual insights. Once a few universal constants were known, he realized that they could be combined to form natural units. Not arbitrary units, not local standards, not cultural habits dressed up as necessity, but scales that would mean the same thing to any intelligent beings anywhere in the cosmos who had discovered the same laws. In that sense, natural units are almost like the universe, introducing itself without translation. They do not depend on the size of a king's foot, the dimensions of a metal bar in a vault, or the administrative preferences of a committee. They emerge from the structure of nature itself. To build the Planck mass, physicists begin with 3 ingredients, each carrying a different piece of the universe's grammar. One comes from relativity and tells us about the role of light and the structure of space-time. One comes from quantum theory and tells us that action at the microscopic level is not smooth and arbitrary, but comes with a fundamental graininess. And one comes from gravity and tells us how strongly matter and energy influence space-time. Taken separately, these constants belong to very different stories. Combined carefully, they reveal the scale where those stories stop being separate. That is one of the quiet marvels of theoretical physics. You take constants discovered in different contexts, One from the behaviour of light and space-time, one from the early quantum revolution, one from gravity, and by asking how they can be joined into a quantity with the dimensions of mass, you uncover a scale that points toward the unfinished frontier of physics. Not bad for what sounds at first like dimensional bookkeeping, and that is worth stressing. Dimensional analysis, when done properly, is far more than a tidy classroom exercise. It is often a way of hearing structure before one fully understands the music. Let us linger with those ingredients in spirit, because each one deserves a little attention before we watch them work together. The relativistic ingredient comes from the constant speed of light, which is not merely about light in the everyday sense. It is one of the central conversion factors in the architecture of space-time. It links space and time, sets the causal speed limit of the universe, and enters deeply into the relationship between mass and energy. It is not just the speed of one phenomenon among many. It is part of the geometry of physical law. The quantum ingredient comes from Planck's constant, which announced to physics that the microscopic world is not infinitely smooth in the old classical manner. It sets the scale of quantum effects. Whenever this constant matters significantly in a problem, the world begins to behave in ways that classical intuition cannot comfortably digest. Uncertainty becomes unavoidable, discreteness enters. Fields and particles begin acting like one another in ways that make ordinary language sweat slightly. The gravitational ingredient comes from Newton's gravitational constant, the quantity that measures the strength of gravity in the familiar classical description. It tells us how strongly masses attract one another. Compared with the other interactions, gravity is astonishingly weak at ordinary particle scales, and this constant carries that weakness inside it. It is the quiet ingredient, the one that often seems almost too modest to matter in quantum problems until, at the Planck scale, it suddenly becomes impossible to ignore. Now, why should these three be combined at all? Because each represents one of the pillars of modern physics: relativity, quantum theory, and gravity. Most of the time, we can get by with 2 out of the 3, or even 1, depending on the situation. For fast-moving but not quantum systems, relativity may be enough. For atoms and particles at moderate energies, quantum theory may dominate while gravity is ignored. For planets, stars, and galaxies, gravity and relativity take center stage while quantum details recede. But if there is a scale where all 3 pillars must be included at once, then it should be possible to estimate that scale using all 3 constants together. And that is exactly what happens. By combining them so that the resulting quantity has the dimensions of mass, physicists define the Planck mass. Nothing in this construction refers to any particular particle, material, or experiment. It is not derived from the properties of gold or hydrogen, or your least reliable kitchen appliance. It comes from the universal constants themselves. In that sense, it is almost unsettlingly pure. The universe, through the language of its laws, offers a mass scale that says quite plainly, if you reach this region, the separate simplifications you have relied on will begin to fail. One of the pleasures of this construction is that it shows how much can be learned before one possesses a complete theory. Physicists do not yet have a fully accepted and experimentally verified theory of quantum gravity. The final framework remains elusive, yet the Planck mass can still be identified because the constants already tell us where the trouble should begin. It is a forecast rather than a final explanation, a sign on the road rather than the full map of the city ahead. That kind of knowledge is common in physics. One often knows where a theory will break down before knowing precisely what replaces it. There is also something deeply satisfying in the fact that the Planck mass does not emerge from sheer mathematical whim. It carries physical meaning because each of its ingredients represents a genuine limit or structure in nature. The speed of light marks the relativistic structure of space-time. Planck's constant marks the onset of quantum behavior. The gravitational constant marks the strength of gravity. Put them together, and you are effectively asking, at what mass scale do relativity, quantumness, and gravitation become equally unavoidable? The answer is the Planck mass. Now, Here, the universe does one of its more entertainingly inconvenient things. The resulting mass is not absurdly large in human terms. It is tiny by ordinary standards. You would not need a crane, a suspension bridge, or a prayer circle to deal with it physically. But in the world of particle physics, it is enormous. This is the same oddity we met earlier, but the construction now helps explain why it matters. The Planck mass is large not because it would crush a table, but because it towers over the masses of known elementary particles. It lies far beyond the energy scales we routinely probe. That gulf is one reason gravity feels so weak in particle experiments. Ordinary particle masses are nowhere near the scale where gravity becomes naturally competitive with quantum effects. This is an important point, and one that deserves to be said slowly. The weakness of gravity at familiar particle energies is not just an isolated annoyance. It is reflected in the size of the Planck mass. The fact that this mass scale is so high relative to known particles means that reaching the regime where quantum gravity becomes direct is extraordinarily difficult. Nature has set the threshold very far away from the energies of atomic and subatomic life, as we usually encounter them. That is why the standard model can ignore gravity so successfully in most contexts. It is not because gravity is unreal, it is because the natural mass scale of quantum gravity is so much larger than the masses we deal with in ordinary particle physics. Another way to think about the construction is to ask what happens if one tries to localize a particle within a smaller and smaller region. Quantum theory tells you that tighter localization requires greater uncertainty and momentum, which means larger associated energies. Relativity tells you that energy and mass are deeply linked. Gravity tells you that enough energy concentrated in a small enough region will curve spacetime significantly. So there must be some point where the energy required to probe a tiny region becomes enough to make the gravitational effects of the probe impossible to neglect. The Planck mass is tied to that point. It is one of the ways the universe tells you that there is no such thing as a completely innocent measurement at arbitrarily small scales. That idea has a remarkable philosophical flavour to it. We often imagine knowledge as the gradual removal of distance between observer and object, as though one can keep refining one's lens forever without changing the thing being examined. The Planck scale challenges that dream. It suggests that at sufficiently high energies, the act of probing no longer reveals a passive underlying stage. It shakes the stage. It may even damage the stage badly enough that the old concept of stage ceases to apply. The Planck mass, constructed from universal constants, carries that warning in condensed form. There is a reason physicists trust such constructions even when the full theory is missing. Nature has rewarded this style of reasoning many times before. Long before a complete quantum theory of matter was available, rough scales and constants hinted where classical reasoning would fail. Long before detailed nuclear models matured, dimensional arguments suggested characteristic energies and sizes. The universe often gives advance notice in the form of scales. It does not always explain itself fully at once, but it leaves signposts. The Planck mass is one of the clearest signposts we possess, and because it belongs to a larger family, it gains additional force from its relatives. The same constants that define the Planck mass also define the Planck length and the Planck time. These are fantastically small. The Planck length is so tiny that ordinary intuitions about distance simply stop being useful. The Planck time is so brief that everyday language about succession and duration begins to feel clumsy. Together with the Planck mass, these scales suggest a regime where the smooth continuum of space-time may no longer be a valid description. If the Planck length marks the distance scale of quantum gravitational structure, then the Planck mass marks the energy scale required to make that structure relevant. This is where the construction begins to feel more like revelation than arithmetic. By combining three constants from three major theories, one discovers not just a number, but a whole region of conceptual instability. The Planck mass says how much energy is needed before gravity joins the quantum dance in earnest. The Planck length says how small the dance floor becomes before its boards may stop being smooth. The Planck time says how brief the steps become before our normal sense of temporal order may need reinterpretation. We do not yet know the choreography, but we know the old one will not survive unchanged there. It is also worth noticing what the Planck mass does not depend on. It does not depend on the details of chemistry. It does not depend on the existence of planets, stars, or life. It does not depend on the accidental masses of electrons or quarks, or the history of our experimental tradition. It emerges from the deepest universal constants we know. That gives it a kind of dignity. It is not merely one scale among many discovered by empirical accident. It is a natural unit of the cosmos, whether or not anything in the present universe happens to sit neatly at that mass in the form of a stable elementary particle. This can be a little confusing at first because the word mass encourages us to look for an object, but the Planck mass is better understood as a threshold in the structure of law. It tells us where certain approximations die. Below it, quantum field theory on a fixed background usually works well. Above it, or even approaching it conceptually, one expects the background itself to become dynamical in a quantum sense. That is a profound shift. It means the very arena in which physics is usually written becomes part of the uncertain story. One might say the Planck mass is where nature stops allowing us to keep our categories tidy. Mass, energy, geometry, and quantum uncertainty all begin crowding into the same conversation. The classical idea of spacetime as a smooth stage and the quantum idea of particles and fields fluctuating upon it can coexist comfortably only so long as the energies stay far below this natural scale. Once the Planck mass is relevant, the coexistence becomes strained. There is, of course, an irony in all this. Human beings are very fond of units because units make the world manageable. They allow bridges to stand, medicine to be dosed, clocks to agree, and recipes to avoid catastrophe most of the time. Yet the most revealing units in theoretical physics are often those that expose the limits of manageability. The Planck mass is a unit that tells us not how comfortably the world fits our measuring systems, but where our best theories begin to exceed their remit. It is a unit of conceptual humility, and yet it is also a unit of hope. Because once a scale is known, the search can be focused. One knows what a deeper theory must somehow respect or explain. A theory of quantum gravity, whatever form it ultimately takes, must account for the significance of the Planck scale. It must explain why these constants combine as they do, why known particle masses lie so far below that threshold, and what really happens to space-time and matter when the Planck mass becomes physically relevant. The scale does not solve those problems, but it frames them with admirable clarity. In a way, building the Planck mass from fundamental constants is like discovering the outline of a hidden country by reading the pressure in the air. You have not yet walked its roads or seen its cities. You do not know its full geography, but you know it is there because the surrounding conditions demand it. Relativity, quantum theory, and gravity cannot all be fundamental in the forms we currently use without eventually meeting under extreme conditions. The Planck mass tells you where that meeting ought to matter. This is one reason the subject retains such fascination. It is not just a technical definition for specialists to mutter about at conferences while looking meaningfully at diagrams. It is a distilled statement about the unfinished business of physics. Classical gravity and quantum theory both work magnificently in their proper domains. The Planck mass is the scale where those domains threaten to overlap too strongly for separate treatment. It is the place where our confidence becomes conditional. If we were creatures who had evolved at Planckian energies, perhaps none of this would seem strange. We might regard smooth space-time as a quaint large-scale illusion and think of quantum geometry as obvious common sense. We might look at planets and chairs the way we look at clouds, as crude averages hiding the real microscopic drama. But we are large, warm creatures living very far from the Planck scale. Our intuitions were trained on middle-sized objects moving slowly and rarely exploding. So when physics builds a mass scale from nature's deepest constants and tells us that this is where space-time itself may become quantum, we feel the strain. The strain is not in the mathematics alone. it is in our imagination. Still, imagination can be educated. That is one of the quieter pleasures of subjects like this. What begins as a baffling phrase gradually sharpens into a meaningful idea. The Planck mass is not a mysterious object, but a natural scale built from the constants of relativity, quantum theory, and gravity. It marks the threshold where those three domains become inseparable. It explains, in part, why gravity is so weak in the world of known particles, and it warns us that beyond a certain energy, the familiar ways of carving up reality into background and contents, stage and actor, geometry and field may no longer hold. From here, the obvious next step is to ask why this scale feels so oddly large from the perspective of quantum physics. Why should the mass associated with quantum gravity be so enormous compared with ordinary particle masses? Why is the gulf so wide? Because once the Planck mass has been built from the constants, one immediately notices the mismatch. Nature has placed the scale of quantum gravity immensely higher than the scale of the particles we know, and that is not a decorative curiosity. It is one of the deepest clues we have about why gravity behaves as it does in the microscopic world. There is a peculiar moment that arrives once the Planck mass has been introduced properly. Up to that point, it can sound like one more impressive but remote label in theoretical physics, the sort of term that floats through documentaries and lecture halls wearing an air of importance, and hoping no one asks it to explain itself too plainly. But once you understand that it is built from the deepest constants of relativity, quantum theory, and gravity, another question pushes its way forward almost immediately. Why is it so enormous compared with the masses of the particles we actually know? Why is the scale associated with the breakdown of our current descriptions so fantastically far above the ordinary quantum world? That question matters because the answer is not merely that nature felt like being difficult, though one must admit that nature often gives that impression. The largeness of the Planck mass in particle terms is one of the clearest signs that gravity is fundamentally unlike the other interactions we deal with in quantum physics. It explains why gravity can shape galaxies and stars with such authority, while remaining almost laughably irrelevant in most particle experiments. It also tells us why the route to quantum gravity has been so hard to walk. The threshold is simply very far away from where the rest of quantum field theory lives comfortably. To feel the strangeness of this properly, it helps to compare the Planck mass not with familiar human-scale objects, but with the masses of elementary particles. In daily life, the Planck mass is tiny. It would not alarm a grocer, threaten a bookshelf, or persuade anyone to reinforce the floorboards. But particle physics is not daily life, and that is where the confusion often begins. Compared with an electron, a proton, a neutrino, or even the heavier unstable particles created in accelerators, the Planck mass is colossal. It is not a little larger. It is not modestly bigger in the way a suitcase is bigger than a loaf of bread. It is separated by an immense gulf. If the masses of known particles are the usual cast of a chamber performance, the Planck mass arrives like a cathedral organ being pushed on stage during a string quartet. That mismatch is not decorative. It is the reason gravity is so weak in the quantum world. This point is worth dwelling on, because gravity's weakness is one of those facts that can become too familiar to feel shocking. We say it often enough that it begins to sound like a mere property on a list. Strong force, electromagnetic force, weak force, gravity, and gravity happens to be the feeblest by many orders of magnitude. Fine. Onward we go. But really, this is one of the greatest symmetries in all of physics. Gravity is not just a bit weaker than the others, it is absurdly weaker at particle scales. So weak in fact that when particle physicists calculate interactions among fundamental particles, gravity is usually left out entirely without any practical loss. One can study the collisions, decays, and quantum behavior of particles to exquisite precision while pretending gravity is not in the room. Because in that room, for those purposes, it barely is, and yet the same gravity rules the large-scale structure of the cosmos. It gathers gas into stars, stars into galaxies, and matter into the web of the universe. It curves space-time, governs orbits, creates black holes, and quietly determines the overall architecture of the visible heavens. The weakness of gravity at the microscopic level is therefore not the weakness of something unimportant. It is the weakness of something that becomes overwhelming only when enough mass and energy accumulate. In a sense, gravity is the great collectivist of the forces. It rarely dominates the individual quarrel, but it wins the population count. The Planck mass tells us where this changes. It marks the scale at which gravity would no longer be feeble in a quantum setting. If a particle or process had energy on the order of the Planck mass, gravitational interactions would become as important as the other quantum effects, and the usual habit of treating spacetime as a passive background would begin to fail. But because the Planck mass is so much larger than the masses of known particles, we remain, in most experiments, comfortably below that threshold. Quantum theory thrives. Gravity sulks in the corner and waits for stars. There is a simple conceptual reason why the Planck mass being huge makes gravity weak. When a characteristic scale associated with an interaction is very high, compared with the energies available in a process, that interaction tends to appear weak at lower energies. The influence is suppressed. The farther below the scale you live, the less directly you feel the interaction in a quantum setting. In this case, the characteristic scale is extraordinarily high by the standards of particle physics, so gravity is extraordinarily hard to excite in any meaningful microscopic way. The theory is effectively telling us that unless you reach very high energies indeed, gravity will remain a faint correction rather than a leading actor. That is why a proton in a collider does not behave like a tiny black hole. That is why electrons do not curve space-time in any noticeable laboratory sense. That is why atoms do not need quantum gravity corrections to explain chemistry. The Planck mass towers so far above these systems that gravity's quantum role becomes negligible. It is not absent in principle. It is suppressed by the sheer remoteness of the relevant scale. Now, this remoteness raises a deeper and more unsettling question. Why should the Planck mass be so high at all? Why should the natural scale of quantum gravity stand so far above the scale of the particles and interactions described by the Standard Model? This is related to what physicists often call the hierarchy problem, though that phrase is used in several related ways and comes with its own theoretical baggage. The core unease is straightforward enough. If the Planck mass is the natural scale of gravitation in quantum theory, why are the masses of known elementary particles so tiny by comparison? Why is there such an enormous gap between the electroweak scale and the Planck scale? That gap does not merely offend our aesthetic sense, though physicists are not entirely immune to aesthetic grievances. It matters because quantum field theories are often sensitive to very high energy scales. Parameters in the low-energy world can receive contributions from physics at much higher energies, and keeping those low-energy values stable can require delicate cancellations or protective symmetries. In plain terms, if the Planck scale is so huge, then one wants to know why the much smaller particle masses and interaction scales of the Standard Model remain where they are without being dragged upward or destabilized by the high-energy structure beyond them. This is one reason so many theoretical ideas flourished over the last several decades. Supersymmetry promised, among other things, a way to protect the Higgs sector from dangerous corrections and keep the electroweak scale naturally below the Planck scale. Extra-dimensional models suggested that perhaps gravity only appears weak because it spreads into dimensions hidden from ordinary matter, making the true fundamental scale lower than it seems. Technicolor, compositeness, warped geometries, anthropic arguments, and other frameworks each attempted in their own way to explain why the Planck scale is so far removed from the masses we observe. So far, nature has not rewarded any one of these ideas with decisive confirmation, which is both disappointing and very much in character. Still, even without a final explanation, the sheer size of the Planck mass teaches us something immediate. It teaches us that the world of known quantum particles sits in a kind of low-energy valley very far beneath the mountain of quantum gravity. That valley is the domain in which the standard model operates brilliantly. Here, fields and particles can be treated on a fixed space-time background. Here, renormalized quantum field theories behave with astonishing predictive success. Here, gravity is an afterthought. But the mountain remains in the landscape. It is not gone. It is simply distant. One can also approach the issue from the angle of localization and probing. To examine smaller and smaller distances, one must typically use higher and higher energies. That much is already familiar. But as the energy of your probe increases, so too does its gravitational significance, because energy contributes to gravity. At ordinary accelerator energies, this effect is negligible. One can cram vast energies by human standards into a tiny collision without worrying that spacetime itself is becoming dynamically unstable. But if one could somehow continue pushing upward toward the Planck mass, a point would come where this carefree attitude ends. The energy required to resolve a tiny region would itself curve spacetime significantly. The instrument of investigation would begin to distort the thing being investigated in a fundamentally gravitational way. This is another expression of why the Planck mass must be huge if gravity is to stay weak in the ordinary quantum world. If the threshold were much lower, then high-energy particle physics would already be full of strong gravitational surprises. Every sufficiently violent collision might trigger mini black holes or quantum geometric distortions. Every precise attempt to localize a particle might become tangled with gravitational collapse. The smooth background picture of quantum field theory would break far earlier than it does. The fact that we can successfully perform ordinary quantum experiments without such complications tells us that the gravitational threshold is extremely high. The Planck mass is huge because the world we inhabit is, in particle terms, comfortably far from the direct reign of quantum gravity. There is something subtly reassuring in that, though also frustrating. Reassuring because it explains why our existing theories work so well where they do. Frustrating because it places the next layer of fundamental physics so far beyond our direct reach. We are rather like natural philosophers who have beautifully mapped the coastline and inland valleys of a great continent, while knowing that the high northern ice fields hold crucial answers but are separated from us by terrain we cannot yet cross. The Planck mass tells us where the ice begins. It does not provide the boots. Another way to see the size of the gap is to compare gravity with electromagnetism at the level of simple particles. The electric repulsion between two electrons is fantastically stronger than their gravitational attraction. This is not because electricity is merely somewhat more energetic. It is because the gravitational coupling at such low masses is incredibly tiny. If the relevant gravitational scale were closer to ordinary particle masses, the comparison would look very different. Charged particles might interact through gravity and electromagnetism on more comparable terms. Atomic structure would be transformed. Chemistry would likely be unrecognizable. Stable matter as we know it might not exist in anything like its present form. The hugeness of the Planck mass, then, is tied not just to an abstract theoretical problem, but to the very possibility of a world where gravity can dominate the cosmic, and yet politely leave atoms to their own business. This separation of scales is one of the reasons physics can be organized at all. Different domains become describable by effective theories, each valid within a range. We do not need quantum chromodynamics to calculate the trajectory of a football, and we do not need quantum gravity to explain the hydrogen spectrum. The Planck mass stands so high above most of particle physics that it permits this layering. It allows the lower energy world to develop its own structures, symmetries, and approximations. One might say it gives the universe room to specialize, and yet the very existence of such a dramatic separation remains conceptually provocative. Why should the basic structure of nature allow such a vast hierarchy? Is it brute fact? Is it the result of some deeper symmetry? Is it environmental selected in a multiverse because worlds with very different hierarchies do not produce complex structures or observers? Is it evidence that our notion of the Planck scale as fundamental will itself be revised? these questions remain very much alive. The Planck mass is huge for the quantum world, but whether that hugeness is a deep principle or a clue to deeper hidden machinery is still uncertain. There is also a historical irony here. Early quantum physics taught us to expect that the very small would be the domain of low masses, tiny effects, and subtle granularity. Then the Planck mass arrives and says, not so fast. The very small, when combined with gravity, may require enormous energy scales. The microscopic does not always mean the lightweight. To reach the shortest meaningful scales, one may need the heaviest quantum probes. The smallest stage demands the heaviest actor. That is not a contradiction. It is one of the central lessons of the subject, and once you accept that lesson, many things begin to fall into place. Gravity is weak in ordinary quantum processes because the natural mass scale governing its quantum importance is huge. The Planck mass is huge because the constants of nature place the gravitational threshold far above the known particle masses. The hierarchy between the standard model and quantum gravity is therefore not a side detail. It is the reason the two domains can often be treated separately. It is also the reason unifying them has proved so difficult. The most direct experiments we know how to do take place deep in the valley, while the crucial physics may live on the mountain. None of this means the Planck scale is irrelevant until one literally reaches it. High-scale physics can leave indirect fingerprints. It can influence the structure of effective theories, the running of couplings, cosmology, black hole thermodynamics, early universe conditions, and subtle theoretical consistency requirements. But the direct collision of gravity and quantum field theory, the moment when one can no longer politely ignore either, is tied to the Planck mass precisely because that mass is so much larger than the ordinary quantum masses we handle. So the hugeness is not an embarrassment to be explained away before one can continue. It is the whole reason the story takes the shape it does. The Planck mass, being immense for the quantum world, means gravity spends most of its time below the threshold of microscopic relevance. It waits until energies become extreme, distances become tiny, and space-time itself is forced into the conversation. Only then does it stop whispering. From here, the natural next step is to ask what happens when gravity does stop whispering. What sort of world appears when the energy scale rises far enough that gravity can no longer be left outside the quantum drama? Because once the Planck mass is understood as the high threshold that suppresses gravity in ordinary particle physics, the obvious question becomes what lies at the threshold itself. What changes when gravity refuses to stay weak any longer? For most of the physical world we know directly, gravity behaves with a kind of deceptive modesty. It is always there, of course. It keeps us on the ground, guides the moon, shapes planets, builds stars, and gathers galaxies into long, delicate structures that stretch across the cosmos. It is the great architect of large things, and yet when we move down into the microscopic world, into the realm of atoms and particles and quantum fields, gravity becomes so faint that one can almost forget it has shown up at all. The equations of particle physics proceed quite happily without it. The interactions that matter are electromagnetic, weak, and strong. Gravity is like a distant relative at a noisy family gathering, present in the official seating plan but inaudible over the actual conversation. That arrangement is so familiar that it can begin to feel inevitable. One might easily imagine that gravity simply belongs to the world of large accumulated masses and has no real claim on the quantum world beyond a symbolic one. But the Planck mass tells us otherwise. It tells us that gravity is not absent from the microscopic world, because it is fundamentally irrelevant there. It is absent because the energies we usually reach are nowhere near high enough to force it into the foreground. Raise the energy far enough, compress it into a small enough region, and gravity stops being shy. It stops accepting a minor role. It pushes into the centre of the problem and begins altering the stage itself. That is the threshold we're approaching now in the story. What happens when gravity refuses to stay weak? The first thing to understand is that this refusal is not a mood change. gravity does not suddenly become a different interaction with a more assertive personality. Its apparent weakness depends on scale. At low energies and for ordinary particle masses, gravitational effects are extraordinarily suppressed. But as the relevant energy approaches the Planck scale, the suppression fades. The comparison changes. Gravity begins to stand shoulder to shoulder with the other ingredients in the quantum problem, and once that happens, many of the assumptions that made ordinary quantum field theory so successful start to wobble. In normal particle physics, one works with a fixed background spacetime. The stage is taken as given. Fields live on it, particles emerge from the fields, interactions occur, and the geometry itself remains calm and classical in the background. Even when the interactions are wildly energetic by laboratory standards, space-time does not mind very much. It stays smooth. It provides coordinates. It supports causal structure. It does not demand center stage. That is what allows so much of quantum theory to be formulated so precisely. The world may be probabilistic and full of fluctuating fields, but the arena in which those fluctuations take place is treated as stable. The moment gravity becomes strong in the quantum sense, that separation begins to fail. This is the key shift, and it is more profound than simply adding one extra force to a list. If gravity were just another interaction like electromagnetism, one might imagine quantizing it in a straightforward way and carrying on. But gravity is different because it is tied to space-time itself. In Einstein's picture, gravity is not merely something that happens within geometry. It is geometry responding to matter and energy. So when gravity becomes strong at tiny scales, it is not just that particles begin attracting one another more noticeably. The very structure of distance, duration, and background order may become unstable or uncertain. The stage is no longer passive. It becomes dynamical, fluctuating, perhaps even granular in some deeper sense we do not yet fully understand. This is one of the reasons the Planck scale is so significant. It is where the ordinary background picture can no longer be trusted. To say gravity refuses to stay weak is to say that the classical smoothness of space-time can no longer be treated as safe from the quantum disturbances of matter and energy. The geometry joins the argument. Coordinates lose some of their innocence. The familiar distinction between contents and container starts to blur. A useful way to picture this, at least initially, is to think about trying to inspect smaller and smaller regions of space. To do that, one generally needs higher and higher energies. That is standard quantum reasoning. Finer resolution requires more energetic probes. Up to a point, this works beautifully. We have learned immense amounts about matter by smashing particles together at extraordinary speeds and reading the debris. But every increase in energy comes with a hidden passenger. Energy gravitates. It contributes to the curvature of space-time. So the more aggressively you probe, the more gravitational influence you introduce into the system. Most of the time, this influence is negligible. Near the Planck scale, it is not. At that point, the act of examination becomes part of the gravitational problem. One is no longer shining a torch on a tiny object from a safe distance. One is throwing such immense energy into such a small region that the geometry itself may bend sharply in response. The probe disturbs the target in a fundamental way, not simply by transferring momentum or altering a quantum state, but by changing the space-time setting in which the target exists. This is where ordinary intuition runs into trouble. We like to imagine measurement as a form of increasingly gentle or increasingly precise inspection. Quantum theory already taught us that measurement is not so innocent. The Planck scale adds a further twist by suggesting that sufficiently precise probing may also become gravitationally destructive. One of the most dramatic possibilities here is the formation of tiny black holes. Now, one must be careful with this idea because it has a habit of escaping into popular science in ways that are either too breathless or too casual. The basic point, however, is simple enough. If enough energy is packed into a sufficiently small region, gravity may become so intense that the region collapses behind an event horizon. The system you intended to use as a microscope turns, in effect, into a black hole. You try to look more closely and instead create an object that hides the very region you were trying to inspect. That possibility is conceptually striking because it suggests a limit to operational meaning. Below a certain scale, or rather beyond a certain concentration of energy, ordinary notions of spatial localization may stop being physically meaningful, not because the universe is forbidding knowledge out of spite, but because the tools required to define such tiny regions undermine the regions themselves. You do not reveal smaller structure, you produce gravitational collapse. The question of what lies inside becomes tangled with the fact that the inside may no longer be accessible in the ordinary sense. This is one reason the Planck length is often discussed alongside the Planck mass. The mass tells you the energy scale where gravity becomes quantum relevant. The length tells you the distance scale where space-time may cease to behave like a smooth continuum. Together they suggest that there is a threshold beyond which closer inspection does not simply mean finer detail. It means a different kind of reality, one in which geometry and quantum uncertainty cannot be disentangled. Once gravity refuses to stay weak, another familiar idea also becomes unstable, namely, the idea that one can treat interactions as happening in a pre-existing temporal order without worrying too much about time itself. In ordinary quantum mechanics and quantum field theory, time is often treated as a given parameter. Things evolve in time, states change with respect to time. Even when probability and uncertainty complicate matters, time is still a relatively dependable coordinate in the background. But in general relativity, time is part of the geometry. It can stretch, slow, and depend on gravitational conditions. So if gravity becomes strongly relevant at the quantum level, the very notion of a clean background time parameter becomes questionable. Time may no longer be an unquestioned stage direction. It may become part of the quantum drama too. That is one reason the search for quantum gravity is so difficult. The theories we have are built with different assumptions about what is fixed and what is dynamical. Quantum field theory assumes a background space-time. General relativity denies that space-time is fixed in any absolute sense. When gravity is weak, the contradiction can be ignored because space-time fluctuations are negligible. When gravity becomes strong, the contradiction becomes impossible to overlook. One needs a framework in which geometry itself can be treated in a quantum manner, and that turns out to be a much harder task than simply quantizing one more field in a prearranged arena. There's also a subtle but important emotional shift in the physics once gravity enters this regime. In most of science, stronger effects mean clearer signals. Turn up the strength, and the phenomenon becomes easier to see. But with gravity near the Planck scale, stronger does not simply mean clearer. It means more conceptually invasive. The interaction is not just another contribution to a scattering amplitude. It threatens the definitions of the very observables you hope to calculate. Strong quantum gravity may not merely alter the numbers, it may alter the meaning of the questions. This is where many theoretical approaches begin to part ways, each trying in its own style to answer what really happens when gravity refuses to remain weak. In string theory, the basic ingredients are not point particles, but extended objects, and this can soften some of the violent short-distance behaviour that point particle theories would otherwise produce. Gravity emerges naturally there, and the ultraviolet troubles are reorganised in a way that may avoid the worst infinities. In loop quantum gravity, one explores the possibility that space-time itself has a fundamentally discrete structure, with areas and volumes quantized in a deep sense. In asymptotic safety approaches, the hope is that gravity may become well behaved at high energies because the theory flows toward a special kind of fixed structure. In causal set ideas, the very fabric of space-time may be built from discrete relations rather than continuous geometry. These programs differ enormously in method and ambition, but they are all trying to answer the same question. What is the correct language once gravity no longer stays weak, and the old separation between geometry and quantum matter collapses? Even without choosing among these approaches, one can already say something definite. ordinary spacetime is likely not fundamental in the way it appears at low energy. That is a startling sentence, and it deserves to be approached with care. It does not mean that tables, chairs, planets, and train stations are illusions. It means that the smooth continuum we use to describe locations and intervals may be an emergent large-scale description, much as a fluid appears continuous even though it is made of molecules. At everyday scales, the continuity works beautifully. At the deeper scales, it may not survive. When gravity becomes strong in the quantum sense, one begins to suspect that space-time itself must be rebuilt from something more basic. There is a certain irony in this. Classical physics once treated space and time as the ultimate stage, immutable and featureless. Relativity then taught us that the stage bends and responds. Quantum gravity hints that the stage may not even be a stage in the final accounting. It may be a large-scale effect of a deeper structure that does not resemble ordinary geometry at all. So when gravity refuses to stay weak, it is not merely demanding equal billing. It is threatening to rewrite the theatre. Black holes loom over this discussion for another reason as well. They are the one place in known physics where gravity is already so strong that the geometry of spacetime becomes extreme. Classical general relativity describes them powerfully, but once one asks about their interiors, their singularities, or the microscopic origin of their entropy, quantum questions flood in. The Planck scale appears repeatedly in these discussions because it marks the region where the classical description can no longer be trusted. Near singularities, near the earliest moments of the universe, and in the deepest puzzles of black hole information, gravity is not staying weak. It is demanding a quantum account. The early universe is another arena where this refusal may have mattered greatly. In everyday life, we are very far from Planckian conditions, but the universe as a whole once passed through stages of extraordinary density and temperature. If we run cosmology backward, the smooth, expanding universe we observe today leads us toward a much hotter and denser past. Classical general relativity alone drives this story toward an initial singularity, a place where curvature becomes unbounded and the classical equations cease to provide meaningful answers. Many physicists suspect that a correct theory of quantum gravity would replace this singularity with something more intelligible, perhaps a bounce, a quantum creation event, a transitional phase, or some other structure not yet fully understood. Again, the message is the same. When gravity refuses to stay weak, classical reasoning alone stops being enough. There is also a practical sadness to all this, though perhaps sadness is too dramatic a word. Let us say a practical frustration. The regime in which gravity becomes strong at quantum scales is so far beyond present laboratory reach that direct experiments are immensely difficult to imagine. This leaves theorists in an unusual position. They know where the breakdown should occur. They know many of the conceptual constraints a successful theory must satisfy. They can test consistency, derive indirect consequences, and study analog systems, but they cannot yet switch on a machine and observe Planck-scale space-time foam in the way one might observe a spectral line or a particle track. The frontier is visible in outline but not yet accessible in the straightforward experimental manner that made earlier revolutions so decisive. Still, there may be indirect clues. Black hole thermodynamics already tells us that gravity, quantum theory, and information are connected in ways we do not fully understand. Cosmological observations may preserve hints of very high-energy physics from the early universe. Precision tests of symmetry, causality, and effective field theory can constrain the forms a quantum gravity theory may take. There are even speculative scenarios in which new physics lowers the effective quantum gravity scale or produces tiny black holes in high-energy collisions, though current evidence has not favoured such hopes. Nature remains impressively unhurried about revealing herself. Perhaps that is why the conceptual side of the subject matters so much. Even when experiments are hard, one can still understand what is at stake. When gravity refuses to stay weak, we lose the luxury of separating the physics of matter from the physics of space-time. We lose the assumption of a fixed background. We lose the simplicity of treating time as a universal external parameter. We may even lose the notion that points in space and instants in time are fundamental ingredients at all. This is not a small adjustment to the equations. It is a demand for a deeper picture of reality. And yet there is something oddly elegant about the demand. Physics often advances by revealing that things we treated separately are actually aspects of a more unified story. Electricity and magnetism turned out to be one field viewed from different circumstances. Space and time turned out to be woven together. Matter and energy turned out to be deeply linked. Now gravity and quantum theory stand before us in a similar posture, not yet unified, but clearly refusing to remain forever apart. The Planck mass marks the scale of their meeting, and the strength of gravity there is not a nuisance. It is the sign that the reunion can no longer be postponed. One can almost think of the low-energy world as an extended truce. Quantum theory describes the contents of the universe with brilliant precision. General relativity describes the large-scale shape of the stage. Because gravity is weak in microscopic processes and quantum effects are negligible in most macroscopic gravitational settings, the truce holds beautifully. But it is still a truce. At sufficiently high energies under sufficiently extreme compression, the compromise ends. Gravity refuses to remain weak, and the old diplomatic arrangement between theories collapses. That is why the Planck scale carries so much emotional charge for theoretical physicists. It is not just another large number or tiny length. It is the place where the unfinished business begins in earnest. It is where we expect our most successful but separately formulated theories to confront one another directly. It is where singularities, black holes, early universe puzzles, and microscopic geometry all begin to converge. It is where the world may stop resembling the conceptual furniture we've inherited from centuries of lower energy physics. From this vantage, the next question almost asks itself: if gravity becomes strong enough that space-time and particle behavior can no longer be treated separately, what exactly is happening at that threshold? What does the boundary look like where particles, energy, and geometry begin to blur into one another? Because once gravity refuses to stay weak, we are no longer merely discussing a stronger version of familiar physics. We are approaching a region where the categories of familiar physics may themselves begin to lose their sharp edges. There comes a point in this subject where the usual nouns of physics begin to feel less like sturdy pieces of furniture and more like labels we have attached to behaviors that happen to stay separate only under ordinary conditions: particle, energy, space-time. In most of physics, these are distinct enough to handle comfortably. A particle is the thing doing the moving or interacting. Energy is the quantity being exchanged, stored, or measured. Space-time is the stage on which the whole business unfolds. That division works well across an enormous range of successful theory. It is how we teach the subject, how we calculate, and how we keep the conceptual machinery from collapsing into one magnificent heap on the floor. But the Planck scale points toward a threshold where that neat division starts to fail. This is not because the terms suddenly become meaningless in all contexts. It is because the assumptions that kept them separate stop holding together under enough pressure. At very high energies and very small distances, particles cannot be treated as simple localized objects without worrying about the gravitational role of the energy used to localize them. Energy cannot be treated as merely something carried by matter or fields without recognizing that it also reshapes the geometry in which the process occurs. Space-time cannot remain a calm background once the fluctuations and concentrations of energy become strong enough to drag gravity directly into the quantum problem. The categories do not disappear, but they start to bleed into one another. That threshold is one of the deepest reasons the Planck mass matters. It tells us where the blurring should begin in earnest. In the ordinary world, the distinction between a particle and the space around it feels intuitive. A pebble sits in a room. A planet moves through space. Even in atomic physics, where particles are really quantum excitations rather than tiny marbles, we still speak as though there is an object on one side and a background on the other. The language survives because it is useful and often very accurate. But even quantum theory already weakens the old boundary. A particle is not a miniature billiard ball with a tiny itinerary and a suitcase full of definite properties. It is better described as an excitation of a field, a structured possibility governed by amplitudes and constraints. Localization is never perfectly sharp. Identity becomes more subtle. The particle is less a little object in space than a pattern in the physical description. So the boundary was already under strain before gravity arrived at full strength. Quantum theory taught us that matter is not made of hard little pellets sitting obediently at points. It taught us that energy and momentum come with uncertainty, that fields fluctuate, that vacuum is not the same as emptiness, and that the distinction between something and nothing is rather less serene than classical physics had promised. Still, throughout all of this, spacetime remains mostly classical in the calculations. Even if the contents of the world become strange, the container behaves itself. That is the compromise that lets ordinary quantum field theory function so brilliantly. At the Planck threshold, the compromise starts to collapse. The simplest route into this is to think again about localization. Suppose you want to identify the position of something with greater and greater precision. Quantum reasoning tells you that more precise localization requires larger uncertainty and momentum, which in practical terms means you must use or involve higher energies. This is not a flaw in your measuring equipment. It is a structural feature of the world. To see smaller things, you need more energetic probes. Up to this point, the story is already familiar. The trouble is that energy is not a passive visitor. In relativity, energy contributes to gravity. That means the very energy you use to sharpen the concept of location also increases the gravitational influence in that tiny region. Push this process far enough, and you enter peculiar territory. The energy needed to resolve a very small distance begins to curve space-time enough that the notion of a clean little region sitting inside a smooth background becomes suspect. The measurement is no longer just interrogating a particle in space. It is altering the geometry around the target and perhaps even the possibility of defining the target independently of that geometry. The particle is no longer cleanly separate from the energetic and geometric circumstances used to reveal it. This is the blur in its most operational sense. The more tightly you try to define the particle, the more strongly the energy of your definition reshapes space-time. What you're identifying and the means by which you identify it become entangled. The object, the probe, and the background stop behaving like separate layers of a simple story. That kind of entanglement is conceptually unsettling, because classical physics trained us to think of the world as made of identifiable parts inhabiting a stable arena. Even quantum theory, for all its strangeness, often retains enough of that arena to keep calculations manageable. But at the Planck threshold, one begins to suspect that the arena itself must be given a quantum description, and once that happens, the distinction between object and background is transformed. A quantum space-time is not merely a classical space-time with a bit of uncertainty sprinkled over it like sugar on porridge. It is something whose structure may be fluctuating, relational or emergent in a deeper way. This is why some physicists speak of space-time foam, though the phrase can mislead if taken too literally. It suggests that at very tiny scales, space-time may no longer be smooth and continuous, but restless, fluctuating, perhaps riddled with transient geometric irregularities. One should not picture a literal bubbly liquid floating beneath the universe like some sort of cosmic bath. The phrase is metaphorical, but it captures an important suspicion. The continuum that works so well at larger scales may dissolve into a more irregular microscopic reality, where distances and durations are not sharply defined in the old way. If so, then the particle concept itself may require revision. After all, what is a particle in a space-time whose geometry is fluctuating quantum mechanically? Ordinary particle definitions often rely on symmetries of background space-time, on notions of stable propagation, and on the ability to separate field excitations from the vacuum in a reasonably clean manner. In strongly curved or dynamically changing spacetimes, even this becomes subtle. In a genuinely quantum spacetime near the Planck scale, it may become much subtler still. The particle could cease to be a fundamental object and become instead an approximate large-scale notion, much as a wave on the sea is a useful pattern, but not the final microscopic truth of water. Energy also changes character in this threshold region. In ordinary settings, we can often speak of energy as though it were a relatively clear quantity assigned to particles or fields against a known background. But in general relativity, even the concept of total energy becomes more delicate because spacetime itself is dynamical. There is no global universal notion of energy that works in every possible curved geometry with the same ease it works in simple flat settings. Once quantum gravity enters, this delicacy grows. If geometry is fluctuating and if time itself is not a fixed external parameter, then the usual definitions of energy may become context-dependent, approximate, or emergent rather than absolute. This is not merely a technical inconvenience. It hints that the familiar triad of particle, energy, and spacetime may not be fundamental categories at all. They may be the low-energy language that works when the underlying structure settles into sufficiently calm patterns. Near the Planck threshold, those calm patterns may fail, and the deeper description may involve relations, information, algebraic structures, networks, strings, loops, amplitudes, or something else not yet fully captured by any existing theory. One of the reasons black holes appear so often in this discussion is that they sit close to the blur even before one reaches the full quantum gravity regime. A black hole can be formed, at least conceptually, by packing enough energy into a sufficiently small region. That already joins particle language, energetic language, and geometric language in an uncomfortable way. You start with matter or radiation. You talk about its energy. Then suddenly the result is an object best described geometrically, in terms of horizons and curvature. What began as a system of fields and particles becomes a space-time structure, and when quantum theory is added through Hawking radiation and black hole thermodynamics, the categories blur even more. Is a black hole a thermodynamic object, a geometric one, a quantum state, an information processor? Annoyingly, it appears to be all of these at once. The Planck threshold can be thought of as the point where that kind of category mixing is no longer exceptional but expected. Below it, one can still often separate the languages enough to be productive. Above it, or truly at it, the separation may become fundamentally artificial. This helps explain why so many candidate theories of quantum gravity take rather radical forms. String theory replaces point particles with extended objects, softening the short-distance picture and weaving gravity into the spectrum automatically. Loop-based approaches suggest that geometry itself may come in discrete chunks, so that area and volume are quantized rather than continuous. Holographic ideas propose that the information content of a region may be encoded on a lower dimensional boundary, an astonishing shift in perspective that makes ordinary spatial intuition look slightly overconfident. Causal approaches suggest that the deepest structure may be one of ordering relations rather than metric geometry. These ideas differ profoundly, but they agree on something essential. The categories inherited from ordinary quantum field theory on a classical background are not enough. There is also a striking lesson here about identity. We're used to thinking that a thing is itself first, and then participates in a setting second. A particle is a particle, and it happens to live in space-time. But at this threshold, the very properties of the particle may depend on geometric conditions, while the geometric conditions depend on energy and quantum behavior. Identity becomes relational. The object is what it is only within a web of interactions and structures that can no longer be neatly disentangled. Physics becomes less like counting separate pebbles in a box, and more like understanding the roles in a dance where the dancers and the floor influence one another at every step. This relational flavour is especially strong in the problem of time. In ordinary quantum mechanics, one usually imagines states evolving with respect to a time parameter. In relativity, time is part of the dynamical geometry. At the Planck threshold, one can no longer safely assume a fixed universal time against which everything else changes. If time itself is entangled with the gravitational field and subject to quantum considerations, then the distinction between evolution and state becomes more subtle. Some approaches suggest that what we call time may emerge from correlations among more basic variables rather than existing as a fundamental flowing background. If that is right, then even the phrase "what happens at the Planck scale" may be less straightforward than it sounds, because happening itself becomes a derived concept. That may seem like the sort of thought that belongs in the middle of the night after too much coffee and insufficient supervision, but it emerges from very concrete tensions in existing theory. The background time of quantum mechanics and the dynamical spacetime of relativity do not fit comfortably together when gravity becomes strong. Something has to give. Either time is more fundamental than general relativity suggests, or less fundamental than ordinary quantum theory often assumes, or both theories are approximations to a framework where the question is posed differently from the beginning. There is a human temptation at this point to ask for a cleaner picture. What exactly is the world made of then? Strings, loops, bits, events, information, geometry. One wants a crisp noun. Physics, inconveniently, may not owe us one. It may be that the deep structure of reality is not most naturally described by the sort of thing language evolved to handle. Our words were built for middle-sized objects at low velocities in weak gravitational fields. They were not designed for discussing a regime where localized excitations, energetic concentration, and space-time structure become mutually defining. The best we can often do is use several partial metaphors, each illuminating one aspect and distorting another. Even so, some broad lessons seem hard to avoid. First, the Planck threshold is not just another high-energy region, where the same basic ontology continues under rougher conditions. It is a domain where the ontology itself may need revision. Second, the distinction between particle and geometry becomes unstable, because localizing energy strongly enough makes gravity dynamically relevant. Third, familiar notions of energy and time depend more heavily on background structure than we often notice, so they too may need reinterpretation when the background is no longer fixed. And fourth, whatever the correct deep theory is, it must explain why the blurred regime gives rise, at lower energies, to the cleaner categories we rely on so successfully in ordinary physics. That last point matters a great deal. The goal is not merely to replace one mystery with another grander mystery wearing more sophisticated shoes. A good theory of quantum gravity must recover the world we know. It must explain why space-time looks smooth at large scales, why particles are useful approximate entities, why energy and causality become well defined in familiar settings, and why the classical and quantum descriptions we already possess work so well where they do. The blur at the threshold cannot be the whole story any more than the molecular chaos of air is the whole story of weather. One needs the bridge from deep structure to emergent order. This is where effective theory becomes a helpful idea. Much of physics works because higher-level patterns emerge from deeper systems in a controlled way. Fluids emerge from molecules. Temperature emerges from collective behavior. Elasticity emerges from atomic arrangements in solids. In the same spirit, space-time itself may emerge from some more fundamental substrate, and particles may emerge as stable excitations or approximate descriptors in that space-time once the relevant conditions are calm enough. The blur at the Planck threshold would then not be a breakdown into nonsense, but a transition into a more primitive level of description from which the familiar concepts later crystallize. That possibility is both humbling and oddly comforting. Humbling because it suggests that the categories we instinctively trust may be provincial, tied to our place in the energy hierarchy of the universe. Comforting because it means the breakdown is not necessarily chaos, it may be deeper order viewed from the wrong scale. There is also a poetic temptation here, though you specifically asked for no abstract phrasing, so let's keep the feet on the ground. What I mean is simply this. The threshold where particles, energy, and space-time blur is not interesting because it is vague. It is interesting because it is precise about the limits of our present distinctions. It tells us that the world may be organized in a more unified way than the categories of everyday theory suggest. The Planck mass does not hand us that unity fully formed. It does something almost as valuable. It tells us where to stop pretending the old separation is final, and once one sees that, several puzzles begin lining up in a single corridor: the black hole information problem, the nature of singularities, the earliest moments of cosmology, the meaning of locality, the fate of time at the most fundamental level, the possible discreteness or emergence of geometry. These are not separate oddities accidentally sharing office space. They all gather near the threshold where the old categories start to blur. From here, the next step is almost unavoidable. If enough energy packed into a tiny region can begin to turn particles into geometry, if localization can threaten collapse, and if black holes already sit on the border between matter, energy, thermodynamics, and space-time, then we need to look more directly at miniature black holes and the edge of physical meaning itself. Because at that boundary, the question is no longer just what theory we write down. It becomes what sort of thing can still be meaningfully said about the world when the tools of observation threaten to produce the very objects that hide what they were meant to reveal. By the time black holes enter this story, they no longer feel like a dramatic detour. They feel inevitable. We began with the Planck mass as a scale where gravity and quantum physics can no longer be kept politely apart. We then followed that scale into a region where particles, energy, and space-time begin to blur. And once one accepts that sufficiently concentrated energy can reshape geometry in a serious way, black holes stop looking like exotic astrophysical curiosities and start looking like conceptual warnings. They stand at the edge of physical meaning because they are what happens when energy, matter, and space-time become so tightly entangled that the ordinary language of observation begins to break down. The large black holes of astrophysics are strange enough. They form when massive stars collapse, or when matter accumulates under extreme conditions. They curve space-time so sharply that not even light can escape once it crosses the event horizon. They sit at the centre of galaxies, power jets, warp time, and generally behave like the universe's answer to anyone who thought gravity was merely a force that made apples fall. But in the context of the Planck scale, it is not the large black holes that matter most at first. It is the idea that miniature black holes might appear when one tries to localize too much energy in too small a region. That idea changes the tone of the whole discussion. In ordinary physics, one expects that probing smaller distances reveals finer structure, better microscopes, more energetic particles, shorter wavelengths. The method improves, the picture sharpens, the hidden details emerge. That has been the great success story of modern physics. Yet black holes suggest a limit to this strategy. If the energy needed to resolve a very small region becomes great enough, then instead of revealing the region more clearly, the probe may collapse it gravitationally. The energy of investigation becomes so intense that it creates the very object that hides what lies within. You try to look more closely and the universe, in effect, closes the shutters. That possibility is not merely dramatic, it is conceptually devastating in the most productive scientific way. It suggests that there may be a threshold below which the ordinary notion of spatial resolution loses meaning. One does not simply continue shrinking the distance under examination, as though reality were an infinitely detailed mechanical diagram waiting patiently to be unfolded. At some point, the attempt to define a smaller region may trigger gravitational collapse. The closer you try to get, the less operationally meaningful the question becomes. Not because there is definitely nothing there, and not because science gives up in a sentimental cloud of music, but because the physical act of asking has become inseparable from the destruction or concealment of the answer. This is where miniature black holes move from speculation to conceptual necessity. Whether or not they are ever produced in accessible experiments, the logic behind them matters. If general relativity is roughly right about how concentrated energy curves space-time, and if quantum theory is roughly right about the energies required for ever tighter localization, then there should be a threshold where the two considerations collide. That collision is one expression of the Planck scale. At or near that threshold, a tiny region packed with sufficient energy could become a black hole in miniature, a little horizon, a little prison of information, a tiny statement from gravity that says the old rules of inspection have expired. This brings us very close to the edge of physical meaning because black holes are not just strong gravitational objects. They are objects that complicate the relationship between observables and reality. In much of physics, if something exists in a system, one assumes that with good enough instruments and sufficient patience, one can in principle observe it, infer it, or measure its effects in a reasonably straightforward way. Black holes spoil that confidence. Their defining feature is precisely that there is a region from which signals do not emerge. There is an inside and an outside separated by a causal boundary. The theory tells us that the interior exists, but the ordinary route to direct empirical access is cut off. Now, science is not undone by hidden interiors. After all, much of good science involves inferring what cannot be seen directly. We infer the inside of stars, the contents of atomic nuclei, the structure of ancient climates, all from effects and traces. The trouble with black holes is sharper. The event horizon is not just a veil. It is a limit imposed by the geometry of space-time itself. The interior is not merely hard to see, it is causally disconnected from the outside observer in the classical theory. That makes the meaning of physical statements about the inside much more delicate. Once black holes are made miniature in thought, this delicacy becomes unavoidable. If every attempt to push to smaller scales risks creating a horizon, then the question of what lies beyond that horizon is no longer a distant astrophysical curiosity. It becomes entangled with the very possibility of defining short-distance structure. The black hole ceases to be a rare cosmic object and becomes a conceptual barrier in the logic of measurement. This is part of why black hole thermodynamics shook physics so deeply. When Bekenstein and later Hawking showed that black holes behave as thermodynamic systems with entropy and temperature, the effect was extraordinary. Suddenly, a purely geometric object in classical relativity acquired statistical and quantum properties. A black hole was no longer just curvature and an event horizon. It had entropy proportional to the area of the horizon, and it radiated quantum mechanically. In other words, black holes sat directly at the intersection of gravity, thermodynamics, quantum theory, and information. They became less like exotic solutions to Einstein's equations, and more like signposts that the deep structure of physics was trying to tell us something urgent. The entropy result was especially shocking because it suggested that the information content of a black hole scales with area rather than volume. That runs strongly against ordinary intuition. We're used to thinking that the amount of stuff or information in a region should scale with how much room it contains. Yet black hole entropy points toward a different rule, one that helped inspire holographic ideas in modern theoretical physics. The lesson seems to be that gravity forces a severer vision of how much information can be stored in a region of space. Once again, black holes appear not merely as objects, but as boundaries on meaning. They constrain what can fit, what can be known, and perhaps even what space itself fundamentally is. This makes miniature black holes even more conceptually potent. If a tiny black hole can arise from concentrating enough energy, then questions about short-distance structure become questions about information bounds, entropy, and horizon formation all at once. The Planck scale is not just where geometry becomes quantum, it is where the informational content of space-time may itself become subject to radically different rules than those we assume in ordinary field theory. The black hole information problem is a particularly vivid expression of this tension. Classical relativity suggests that information can fall behind a horizon, while Hawking radiation originally seemed to imply that black holes evaporate thermally, potentially destroying the detailed information about what formed them. Quantum theory, however, does not like information destruction in that crude sense. The tension between these principles became one of the sharpest paradoxes in modern physics. Does information escape somehow? Is it stored at the horizon? Does the interior behave in a way classical intuition misses? Are our assumptions about locality, unitarity, or space-time itself too naive? The debate is still active, and various insights from string theory, holography, quantum extremal surfaces and related developments have changed the landscape significantly. But the central lesson remains. Black holes reveal that our standard categories for matter, geometry, and information are incomplete when forced together. Near the Planck scale, that incompleteness ceases to be exceptional. It becomes expected. There is also the matter of singularities, those infamous places where the classical equations of general relativity push curvature and density toward infinity. Singularities are often spoken of as though the universe contains literal infinities, in the same straightforward sense that a bucket contains water. That is not quite the right way to think about them. In practice, a singularity is a sign that the theory has run past the edge of its own domain. It is where the mathematical description ceases to produce physically sensible predictions. Classical relativity points towards singularities inside black holes and at the origin of the standard cosmological model. Most physicists suspect that a proper theory of quantum gravity would soften, replace, or reinterpret these singularities rather than preserve them as final features of reality. Miniature black holes bring this issue to the fore in a particularly sharp way. If tiny horizons can form in attempts to probe short distances, then questions about what lies beneath or beyond the horizon and whether classical singularity structure survives become unavoidable parts of any fundamental theory. One is no longer discussing singularities as distant theoretical curiosities inside giant stars that died inconveniently far away. One is discussing them as part of the boundary conditions of meaning itself at the smallest scales. This is where the phrase edge of physical meaning earns its keep. Physics depends on the existence of operational concepts. What can be measured? What can be distinguished? What can be inferred from accessible data? When black holes appear in the logic of measurement, some of those concepts begin to fray. If defining a space-time region too sharply collapses it into a horizon, then what exactly does it mean to say that there is a structure at smaller distances? If no signal can emerge in the ordinary way, what counts as physical distinction there? If the geometry of the region itself is fluctuating quantum mechanically, what becomes of location and time order? These are not philosophical decorations placed around the edges of hard theory. They are the hard theory once gravity and quantumness cease to stay separate. There is a temptation at this point to think that physics is approaching mystical territory, where words fail and one is left nodding slowly into a cup of tea. But that would be misleading. The edge of physical meaning is not the abandonment of rational inquiry. It is the point where rational inquiry becomes more careful about what its terms are allowed to mean. In fact, the history of physics is full of such moments. Classical ideas of simultaneity had to be revised in relativity. Classical ideas of trajectory and certainty had to be revised in quantum mechanics. The Planck regime, with miniature black holes lurking in the conceptual undergrowth, may require a comparable revision of locality, geometry, and information. That is not mysticism. It is theoretical maturity under pressure. One reason miniature black holes fascinate theorists is that they seem to compress several lessons into one image. They tell us that energy is not just an inert tally, but a source of curvature. They tell us that attempts at finer localization can become self-defeating. They tell us that information and geometry are deeply linked, and they tell us that the classical concept of a smooth space-time manifold may not survive unlimited extrapolation downward. All of that is packed into the humble little nightmare of trying to build an ever better microscope and accidentally inventing a horizon instead. The relation to the Planck mass is especially important here. The Planck mass marks the energy scale at which such gravitational collapse becomes conceptually relevant for microscopic probes. Below that scale, black hole formation is not part of the ordinary story of particle interactions. Above or near it, the possibility enters naturally. That is one reason the Planck mass is not just another big number in a list of natural units. It is the threshold where the black hole becomes a microscopic concept, rather than merely an astrophysical one. Once that happens, the border between particle physics and gravitational geometry is no longer just crossed occasionally, it is dissolved. Some speculative theories once entertained the hope that if the true fundamental gravity scale were lower than the conventional Planck scale, perhaps because of extra dimensions or related ideas, tiny black holes might be produced in high-energy colliders. That possibility generated a brief burst of public anxiety and a much longer stretch of patient explanation from physicists who would really have preferred to spend their time on other things. No such black holes were observed, and the ordinary Planck scale remained stubbornly remote. But the episode serves as a nice illustration of how conceptually vivid the idea is. Even people with no desire to learn quantum gravity can immediately sense that a microscopic black hole would mean the rules have changed, and they would. Yet the most interesting change is not the sensational one about danger or collapse. It is the subtler one about emergence. Black hole physics increasingly suggests that spacetime itself may be tied to information in a deeper way than classical geometry alone reveals. Entanglement, horizon entropy, and holographic principles all hint that the fabric of space may be constructed from relationships more primitive than points and distances. In that sense, black holes in miniature are not only barriers, they may also be clues to construction. They do not merely hide what lies beyond. They hint that the language of beyond must change. This is one of the reasons the area law for black hole entropy remains so striking. It suggests that the number of fundamental degrees of freedom in a region with gravity may be controlled by a boundary rather than a volume. If that is even partly true in a general sense, then our everyday intuition about space being filled with independent little chunks of information may be profoundly misleading. The interior may not be fundamental in the old way at all. What we take to be volume could be emergent from more basic boundary structures or entanglement patterns. That would be an astonishing reversal of intuition, and black holes are one of the main reasons physicists take the possibility seriously. The edge of physical meaning, then, is not simply a wall where thought stops. It may be more like a bend in the road, where the old map ceases to be Euclidean, and a different geometry of understanding begins. Miniature black holes occupy that bend. They arise when the energy needed for sharper questions begins to create the very gravitational structures that deny those questions their old form. They turn short-distance physics into horizon physics. They convert localization into entropy bounds. They place information, geometry, and quantum theory into one cramped room and lock the door until we come back with better concepts. There is also something quietly beautiful about the fact that black holes, once treated as the endpoints of collapse and perhaps even the embarrassment of general relativity, have become one of the richest sources of insight into the deepest structure of reality. They began as strange solutions to Einstein's equations. They are now central to discussions of entropy, information, holography, emergence, quantum chaos, and the nature of spacetime itself. In the context of the Planck mass, they play yet another role. They show that if gravity becomes strong enough on small scales, the universe may stop allowing us to ask for arbitrarily fine spatial detail in the old classical manner. That thought leaves us in an interesting position. We have gone from the Planck mass as a natural unit, to the Planck scale as a threshold for quantum gravity, to the possibility that black holes in miniature mark the limit of ordinary localization, and perhaps the limit of ordinary space-time meaning. This is already enough to show that the Planck mass is not a curiosity but a pressure point in the foundations of physics. But it also forces the next question. If black holes, horizons, and information paradoxes all gather near this scale, what sort of theory could possibly make sense of it all? What lies beyond Einstein and the Standard Model once one fully accepts that neither, on its own, can survive the Planck threshold unchanged? By this point in the journey, it should be clear that the Planck mass is not simply a curious number perched in the margins of theoretical physics, like an ornament nobody quite knows what to do with. It marks the place where two astonishingly successful frameworks cease to cooperate peacefully. On one side stands general relativity, Einstein's great account of gravity, space-time, curvature, and the large-scale architecture of the cosmos. On the other stands quantum field theory, embodied most powerfully in the Standard Model, our extraordinarily precise description of particles and their non-gravitational interactions. Each theory has earned its authority honestly. Each has survived ruthless experimental scrutiny within its own domain. And yet together they remain incomplete. The search for quantum gravity begins exactly there, not because physicists enjoy creating unnecessary complications for themselves, though there are moments when one wonders, but because reality itself seems to require a deeper account than either framework can provide on its own. This is what makes the search so compelling and so difficult. It is not a case of replacing a bad theory with a better one. It is a case of reconciling two magnificent theories that each work brilliantly, where they are supposed to work and yet clash when forced into the same extreme regime. That clash appears near black holes, in the earliest universe, at the Planck scale, and wherever energy, curvature, and quantum uncertainty become too tightly intertwined to keep separated. The problem is not that Einstein was wrong in the usual sense, nor that the Standard Model is somehow sloppy. The problem is that they were built from different conceptual starting points. General relativity makes spacetime dynamical. Quantum field theory usually assumes spacetime as a background. Gravity is geometry in one picture, and just another field candidate in the other, except it refuses to behave like one in all the straightforward ways we might prefer. So the search for quantum gravity is, in essence, the search for a language in which space-time, matter, and quantum behavior can all be described without contradiction when the old low-energy compromises no longer hold. It is not merely a hunt for a missing equation. It is a search for a deeper framework of description. That distinction matters because one can feel, reading about this subject, that perhaps all physicists need is one extra term in the right place and a few unpleasant infinities politely sent on holiday. But the actual challenge is more serious. It may require us to rethink what space is, what time is, what particles are, and what it means for a theory to be fundamental at all. There is a reason general relativity has resisted quantization in the same easy way other fields have not. When physicists quantized the electromagnetic field, the result was quantum electrodynamics, one of the most successful theories ever written. Similar strategies eventually helped produce the broader framework of quantum field theory, including the weak and strong interactions. These theories are not always mathematically pleasant, but they are manageable. Their infinities can be treated systematically through renormalization. Their predictions can be tested with astonishing precision. But gravity, treated naively in the same style, misbehaves at high energies in a much more severe way. The resulting theory does not remain predictively well controlled in the ordinary sense. It throws up divergences that resist the usual rescue methods. This is not merely a technical nuisance. It is a sign that the straightforward point-particle picture on a fixed background is likely not the full story when gravity becomes strong. One route beyond this impasse is string theory, perhaps the most famous and certainly one of the most ambitious candidates for quantum gravity. In string theory, the basic entities are not point particles but tiny extended objects, strings, whose different vibrational modes appear as different particles. That shift may sound modest, but conceptually it is enormous. Point particles interacting at arbitrarily short distances are partly what create the severe ultraviolet difficulties in a naive quantum theory of gravity. Strings being extended soften those short-distance interactions, and remarkably, once one formulates the theory consistently, a massless spin 2 excitation appears naturally in the spectrum, exactly the sort of object one would associate with a quantum of gravity. In that sense, gravity is not awkwardly inserted from outside. It is built in from the beginning. This is one reason string theory attracted such sustained attention. It does not merely tolerate gravity, it seems to demand it. It also has the appealing feature of unifying different particle types within one larger framework and has led to a rich web of mathematical discoveries and dualities. Over time, it also helped inspire one of the most important ideas in modern theoretical physics, the holographic principle, especially in the form of gauge-gravity duality. In certain settings, a gravitational theory in a higher dimensional spacetime can be equivalent to a non-gravitational quantum theory on its boundary. That is an astonishing claim, and one with profound implications. It suggests that spacetime geometry and gravitational dynamics may emerge from a lower dimensional quantum system in a precise way. If true in sufficient generality, it would mean that the very arena of gravity is not fundamental in the old sense, but encoded in something more basic. And yet string theory is not without difficulties. It naturally lives in higher dimensions, which then need to be hidden or compactified in ways that are not uniquely determined. It has a vast landscape of possible vacuum states, making it difficult to extract a unique low-energy world matching ours. It has not delivered direct experimental confirmation, and because the relevant scales are so high, testing many of its distinctive claims remains extremely challenging. Even so, its conceptual achievements are substantial. It gave physicists concrete ways to think about black hole entropy, holography, duality, and the emergence of space-time. Whether it turns out to be the final framework or not, it has profoundly shaped the search. Quite different in spirit is loop quantum gravity. Where string theory often enlarges the framework by introducing new structures and dimensions, loop approaches begin more directly from general relativity itself and attempt to quantize geometry in a background-independent way. The phrase background-independent matters here. Instead of starting with a fixed space-time arena and placing quantized fields upon it, one tries to formulate the theory so that space-time geometry itself is quantized from the start. In this picture, space may come in discrete chunks, with operators corresponding to area and volume having discrete spectra. Geometry is no longer a smooth continuum all the way down. It has a grain, a weave, not a literal woven cloth of course, though the metaphor is hard to resist, but something that suggests continuity may be emergent rather than fundamental. This is attractive for obvious reasons. If the problem is that classical smooth geometry cannot survive unchanged at the Planck scale, then perhaps the right move is to quantize geometry directly, rather than trying to force gravity into the mold of ordinary background-based field theory. Loop approaches have produced valuable insights, especially in formal treatments of quantum geometry and in certain models of cosmology where the classical Big Bang singularity may be replaced by a bounce or a more regular quantum state. That too is conceptually important. Singularities in classical relativity are widely understood as signs of theoretical breakdown rather than final answers. Any approach that can resolve them in a controlled way deserves attention. Still, loop quantum gravity also faces substantial challenges. Connecting the deep quantum geometry to the familiar large-scale world is not straightforward. Recovering classical space-time smoothly and deriving the standard model in detail remain difficult tasks. And as with string theory, decisive experimental guidance is frustratingly scarce. The theory may be onto something essential about discreteness and background independence, or it may capture only part of the deeper story. The honest position, which is often the least glamorous, is that no candidate has yet won the field outright. There are other approaches too, each with its own style and ambitions. Asymptotic safety explores the possibility that gravity might become well behaved at high energies because its couplings approach a special fixed behavior under renormalization. In plain terms, perhaps gravity does not need to be replaced by radically new objects at all. Perhaps it becomes self-consistent in a subtler quantum field theoretic way than naive perturbative methods suggest. This would be a rather elegant resolution, because it would mean the theory saves itself not by abandoning field theory, but by occupying a particularly well-behaved corner of it. Then there are causal set approaches, which suggest that space-time may be fundamentally discrete, not in the sense of a lattice laid out inside a pre-existing space, but in the sense of elementary events ordered by causal relations. In such views, continuity and metric structure emerge only approximately from an underlying partial order. This is appealing because causality is one of the deepest structural features of relativity. If anything is to survive beneath smooth geometry, causal order is a strong candidate. There are also dynamical triangulation approaches, group field theories, emergent gravity ideas, and various programs that place information, entanglement, or quantum error correction at the heart of space-time's construction. Each tries in its own way to answer the same stubborn question. What is the correct deep description once Einstein's geometry and the Standard Model's quantum fields can no longer be treated as separate layers of reality? One feature shared by many of these programs is a growing suspicion that space-time is not fundamental in the way classical intuition suggests. That is perhaps one of the biggest conceptual shifts produced by the search for quantum gravity. For centuries, even after relativity made space-time dynamic, there remained a tendency to think of it as the basic stage. It bent, yes, but it was still the thing in which events happened. Now, more and more lines of thought suggest that geometry itself may emerge from something deeper, perhaps entanglement patterns, algebraic structures, networks of amplitudes, or relations not naturally expressed in ordinary spatial language at all. The precise details vary, but the direction is strikingly consistent. The search beyond Einstein and the Standard Model increasingly looks like a search beyond space-time as a primitive concept. That does not mean space is an illusion, in the lazy popular sense. It means that the smooth three-dimensional expanse we navigate and the temporal order we inhabit may be approximate, large-scale features of a deeper substrate, just as temperature emerges from molecular motion and elasticity emerges from atomic structure, so geometry may emerge from more primitive ingredients. This possibility has been sharpened especially by studies of black holes and holography. The entropy of black holes scaling with horizon area suggested early on that information and geometry are linked in non-trivial ways. Later, developments in holographic duality suggested that entanglement in a quantum system may actually build up the connectivity of space-time itself. The slogan that space-time is made of entanglement is a simplification, but not an entirely irresponsible one. This is where the search for quantum gravity becomes more than a technical attempt to merge equations. It turns into an inquiry into what the world is made of at the most basic descriptive level. Is the universe fundamentally geometric, algebraic, informational, relational, process-based, something else entirely? We do not yet know. But the inadequacy of our present theories near the Planck scale suggests that the answer is not simply particles moving around inside a smooth pre-existing box. The Standard Model excels at describing quantum fields on spacetime. Einstein excels at describing how spacetime responds to energy and momentum. The deeper theory may need to explain both as emergent from something still more basic. At the same time, any candidate theory has to satisfy a brutal list of demands. It must reproduce general relativity in the appropriate low energy limit, because relativity works spectacularly well for planets, stars, gravitational waves, and cosmology at accessible scales. It must reproduce quantum field theory and the Standard Model where those are known to work, because the Standard Model has passed experimental tests with extraordinary success. It should ideally explain black hole thermodynamics, singularity resolution, and the meaning of spacetime entropy. It must handle causality carefully. It should not casually destroy unitarity or locality without offering a better replacement, and though this is not always said loudly enough, it should help make sense of why the world looks as classical as it does at large scales. That last part is especially important. A theory of quantum gravity cannot just be exotic at the top. It must also explain the calmness below. This brings us to experiment, or rather to the persistent frustration surrounding it. The Planck scale is so high that direct probes are beyond present technology by a vast margin. We cannot simply build a machine large enough and energetic enough to watch quantum spacetime flicker in the lab. That makes the search unusually dependent on consistency, mathematical structure, indirect clues, and extreme astrophysical or cosmological situations. Physicists therefore look for signatures in the early universe, in black hole behavior, in possible tiny violations or deformations of known symmetries, in the structure of effective field theories, in the behavior of scattering amplitudes, and in the deep consistency conditions that any candidate must satisfy. None of this is hopeless, but it does mean the subject proceeds with a different rhythm from a field where one can tune an apparatus this afternoon and collect decisive data by next week. Even so, there has been progress, though it is of a subtler kind than the discovery of a new particle in a detector. Black hole thermodynamics, Hawking radiation, holography, dualities, amplitude methods, and cosmological modelling have all changed the landscape. The search is not wandering in darkness with no landmarks. It is more like moving through a dense fog in which certain structures keep appearing reliably enough that one suspects they belong to the true terrain. Information seems important. Horizons seem important. Entanglement seems important. Background independence seems important. Ultraviolet consistency matters. Emergence keeps returning. None of these themes alone is a final answer, but they recur too often to be ignored. There is also a growing realization that the divide between Einstein and the Standard Model may not be healed by simply attaching one to the other. The deeper theory may reorganize both. It may reveal gravity and gauge interactions as aspects of a broader structure. It may explain particle content through geometric or topological features of a more fundamental setting. It may even alter what we mean by law, state, or observable. Historically, the greatest theoretical advances in physics often did not merely combine previous theories, they reframed them. Relativity did not just add corrections to Newton. Quantum mechanics did not just tweak classical trajectories. So one should not be surprised if the final route beyond Einstein and the Standard Model requires a comparable reframing rather than a neat stitched seam. There is a comforting side to this, if one chooses to see it that way. Physics is unfinished in one of the most interesting places imaginable. We know enough to see the gap clearly, yet not enough to close it with confidence. That gives the subject a peculiar honesty. We can say with real precision where current theories succeed and where they become insufficient. We can identify the Planck mass as the natural threshold where gravity and quantum effects must become jointly unavoidable. We can study black holes, early universe conditions, and formal structures for clues. But we cannot yet say, with final authority, what the correct theory of quantum gravity is. And perhaps that is why the search remains so alive. It is not merely filling in details, it is pressing against the foundations of what we think physical description can be. Are space and time fundamental or emergent? Is information more basic than geometry? Do singularities disappear in the right quantum picture? Are black holes laboratories of deep consistency rather than paradox? Why is gravity so weak at low energies? Why is the Planck scale so far above the Standard Model scales? What fixes the constants? What determines the vacuum? Why does locality work as well as it does when so many clues hint that it may not be ultimate? These are not small repairs to the house of physics. They're questions about the ground beneath it. One can feel, beneath all the formalism, a very old scientific instinct at work here. The instinct that says nature's most successful descriptions should not remain patched together forever, if they point toward a deeper unity. Newton unified terrestrial and celestial motion. Maxwell unified electricity, magnetism, and light. Einstein unified space and time and reimagined gravity. The Standard Model unified broad families of particle interactions within quantum field theory. The search for quantum gravity belongs to that lineage. It is the next demand for coherence. issued by reality itself at the Planck threshold. So when physicists work beyond Einstein and the Standard Model, they are not disrespecting those achievements. Quite the opposite. They are taking them seriously enough to notice where they stop fitting together. They are following the implications of success to the point where success becomes incomplete. That is one of the noblest habits in science. You do not cling to a theory by pretending it explains everything. You honour it by using it until it tells you, clearly and precisely, where it cannot go alone. From here, the final turn in this topic is not toward a tidy resolution, because no tidy resolution exists yet. It is toward reflection. If the Planck mass marks the scale where our best separate descriptions collide, if black holes and quantum gravity hint that space-time may be emergent, and if the search beyond Einstein and the Standard Model is still ongoing, then what does the Planck mass ultimately tell us about reality itself, about the limits of theory, and about the peculiar human project of trying to understand a universe that grows stranger the more carefully we ask our questions? After all this, after tracing the Planck mass from Max Planck's first crack in classical certainty to the frontier where black holes, quantum fields and space-time begin stepping on one another's lines, it is worth slowing down and asking what this strange scale really tells us. Not just as a technical matter, though it certainly is that. Not just as a marker in theoretical physics, though it is one of the most important. But as a clue about reality itself, about the limits of our current descriptions, and about the peculiar way human understanding advances. Because the Planck mass is fascinating not merely because it belongs to difficult equations. It is fascinating because it stands at a boundary where physics becomes unusually honest. Most of science, at least from the outside, looks like the steady accumulation of answers. We discover a law, refine it, extend it, and place another neat stone in the great wall of knowledge. There is truth in that picture, and a great deal of important work really does proceed in exactly that way. But the deeper story is less tidy and much more interesting. Science also advances by discovering the conditions under which its best ideas stop being enough. A theory succeeds, and succeeds magnificently, until one day it reaches a situation where its own assumptions begin to strain. That strain is not failure in the ordinary sense, it is the next invitation. It tells us where the map remains unfinished. The Planck mass is one of the clearest such invitations in all of physics. It tells us, first of all, that reality is not arranged around the convenience of our concepts. We separated gravity and quantum physics because, for a very large range of situations, that separation works. It works so well that one can become emotionally attached to it. Relativity for the large, quantum theory for the small, geometry here, fields there, background and contents, stage and actors. It is all very manageable, very orderly and deeply satisfying. Then the Planck mass arrives and says, in effect, that this arrangement is conditional. Useful, yes. Brilliant, certainly. Final, no. There exists a scale where these divisions lose their clean edges, where our two greatest frameworks stop speaking politely in sequence and begin talking over one another. That is not an awkward detail to be cleaned up later. It is a lesson about reality. The universe is not under any obligation to preserve the categories that were convenient for beings of our size, living at our energies, on our planet, in our era of theory. It permits those categories where they work, and withdraws the permission where they do not. There is something deeply humbling in that. The Planck mass reminds us that physics is not a catalogue of names for things. It is a layered attempt to describe patterns that hold under certain conditions and to understand why they hold. We often begin with the assumption that if we keep pushing downward towards smaller scales, we will find simpler and simpler constituents behaving in ways that are clearer and more elemental. But the Planck mass complicates that dream. It suggests that deeper does not always mean simpler in the ordinary sense. Sometimes deeper means that the framework of the question must change. Sometimes the closer you look, the more your method becomes part of the thing being examined. Sometimes, at sufficient intensity, probing reality no longer reveals a smaller stage, it alters the stage. That lesson has broad philosophical weight, though one need not become grand about it. It simply means that the structure of knowledge may itself be scale-dependent. At human scales, objects feel stable, time feels continuous, and space feels like a quiet container. At atomic scales, those impressions become rough approximations. At relativistic scales, time and space lose their independence. At the Planck scale, the distinction between matter, energy, and geometry may blur so badly that none of those terms remains fundamental in the way we once imagined. Reality does not seem to be arranged as one tidy layer repeated at every level. It is more like a hierarchy of descriptions, each true within a range, each emerging from or failing into others under pressure. The Planck mass also tells us something about limits, and here one must be careful not to confuse limits with defeat. There is a lazy way of hearing this subject that makes it sound as though science has simply run into a wall and started sighing dramatically into the dark. That is not right. The limit marked by the Planck mass is not the end of inquiry. It is the place where one kind of inquiry must mature into another. It says that our present theories are incomplete in a precise and revealing way. That is very different from saying that the world is unknowable. In fact, the history of physics suggests the opposite. Every major theoretical limit, once properly understood, has become fertile. The failure of classical mechanics to explain certain microscopic phenomena opened the door to quantum theory. The failure of Newtonian gravity under extreme precision and conceptual scrutiny opened the door to relativity. The tension between relativity and quantum theory near the Planck scale is not evidence that explanation must stop. It is evidence that a deeper framework is waiting to be found. We may not yet know its final form, but we know enough to describe the pressure point. That already counts as serious progress. There is another kind of limit bound up in the Planck mass, one that feels almost existential if you linger with it too long before bed. It suggests that the act of measurement itself may have a built-in horizon, not a practical horizon, in the sense that our current instruments are inadequate and future ones will be better, though that is true often enough. A deeper horizon, a point at which defining smaller and smaller regions requires so much energy that gravity enters and changes the meaning of the region. This does not mean nature is being coy. It means that what can be meaningfully distinguished may be constrained by the structure of the laws themselves. Physical meaning is not just about imagination or mathematical freedom. It is about what can in principle be operationally established in a world where geometry and energy respond to one another. That is one reason black holes belong so naturally to this story. They are not just extreme astrophysical objects. They are warnings written into space-time. They show us that if enough energy is concentrated in a small enough region, access itself becomes problematic. Information, geometry, and thermodynamics begin to converge. Horizons appear. Entropy scales with area. Causal structure takes on a severity that ordinary intuition was not built to handle. The Planck mass sits near the conceptual threshold where such ideas stop being specialized and start becoming general. It tells us that the world may contain not just hidden details, but hiddenness built into the logic of high-energy inquiry. And yet this does not make physics smaller. In a strange way, it makes it larger, because once you realize that space-time itself may not be fundamental, that geometry may emerge from something deeper, that information and gravitation may be more tightly connected than classical thought ever guessed, the project of physics becomes not narrower but richer. The Planck mass does not close a door. It reveals that there was another door behind the first one all along. It also tells us something about the scale of human success. That may sound an odd thing to extract from a natural unit of quantum gravity, but I think it matters. Consider what it means that beings like us, warm mammals on a middling planet, using brains evolved for social life, tool use, and not falling out of trees, have nevertheless managed to identify a scale at which our own best theories should fail. We have not reached that scale experimentally in any direct way. We have not built the final theory that resolves it. But we've understood enough about relativity, quantum mechanics, gravity, black holes, and information to know where the conceptual fracture lies. That is extraordinary. It is one thing to solve a problem, it is another to see clearly the shape of the unsolved territory beyond. The Planck mass therefore represents a peculiar blend of triumph and incompletion. It proves how far we have come and how far remains. It stands as evidence that physics is not merely collecting data points, but uncovering the architecture of its own limits. The fact that we can even formulate the question of quantum gravity so sharply is itself a kind of intellectual achievement. We may not know the final answer, but we know that an answer is needed, and we know many of the conditions it must satisfy. That is not ignorance in the crude sense. It is disciplined uncertainty, which is one of science's most respectable states. There is a temptation, of course, to want a grand conclusion here, to say that the Planck mass proves space-time is emergent, or that information is fundamental, or that reality is made of strings, loops, relations, or something equally decisive sounding. But the honest thing is gentler than that. The Planck mass does not yet tell us which final theory is right. It does not choose the winner in advance. What it does do is constrain the possibilities. It tells us that any successful theory must explain why gravity is so weak at familiar quantum energies, why black holes possess thermodynamic properties, why singularities signal breakdown rather than final meaning, and how the smooth classical space-time we know emerges from whatever deeper structure becomes relevant at the Planck scale. It tells us that a merely patched version of current theory will probably not be enough. That kind of negative knowledge is often underrated. People like answers. We are less enthusiastic about constraints, requirements, and signs that an old framework cannot go all the way, but in theoretical physics these are often the most valuable clues. Knowing what a future theory must recover where the present one breaks, and which principles are under stress can guide decades of work. The Planck mass is such a guide. It says very clearly that if you want to understand reality more deeply, this is one of the places where your explanation must eventually pass. It also says something about scale and perspective. The human world sits very far from the Planck regime. Our daily lives unfold in a placid middle ground where classical objects, thermodynamic arrows, and weak gravity feel natural. Time passes in minutes, tea cools at an understandable rate, furniture remains reassuringly solid, and nothing in the kitchen is in immediate danger of quantum gravitational collapse. That middle ground is so immersive that it can make the Planck scale feel almost unreal by comparison. But the opposite may in some sense be closer to the truth. The calm macroscopic world is the special case. It is the large-scale emergent order. The Planck regime may be alien to intuition, but it is tied more directly to the underlying structure of the laws. We are the creatures of the approximation, and it is no insult to us to admit it. Indeed, much of science consists in overcoming the provincialism of ordinary scale. We learned that Earth is not the centre of the cosmos, that solid matter is mostly structured emptiness, that time is not universal, that certainty is limited, that energy and mass are deeply linked, and that vacuum is not simple nothingness. The Planck mass adds another possible correction. It suggests that space-time itself, which feels so immediate and unquestionable, may be an emergent convenience rather than the deeper stage. If that turns out to be true, then one more pillar of ordinary intuition will join the long list of things reality did not bother to arrange around our comfort. Still, there is no need to become gloomy about that. If anything, it is part of what makes science worth doing. A universe that yielded completely to first intuition would be much easier to manage and much less interesting to inhabit. The Planck mass, in that sense, is not just a theoretical threshold. It is a reminder that wonder survives precision. Even after centuries of mathematics, telescopes, colliders, satellites, and equations of alarming complexity, the world still contains a place where our understanding becomes tentative. There is still frontier. There is still genuine conceptual risk. There are still questions large enough to resist immediate domestication. That resistance matters. It protects science from becoming merely administrative. If all that remained were refinements to the 6th decimal place of already settled truth, important though such work can be, the broader human meaning of the enterprise would shrink. But the Planck scale keeps alive the older spirit of physics, the spirit that asks not merely how this or that system behaves, but what kind of reality makes such behaviour possible at all. That is a different scale of question. It asks after foundations, not just consequences, and the Planck mass sits right at that level. There's also a kind of intellectual ethics bound up in this. The Planck mass teaches restraint. It teaches that one can be precise without pretending to know more than one does. Modern physics is often accused, especially from outside, of arrogance. There are times when the accusation is not entirely baseless. Every profession produces its own forms of overconfidence, but at its best, physics is disciplined by reality. It says what works, where it works, and where it no longer does. The Planck mass is part of that discipline. It marks a point where theoretical honesty must increase, not decrease. One cannot simply extrapolate forever and hope the universe will be too polite to object. In that way, the Planck mass becomes almost a symbol of scientific maturity. It is the recognition that our greatest successes are also finite. Not false, not discarded, not trivialized, but finite. General relativity is magnificent. Quantum field theory is magnificent. Their overlap remains unfinished. That is not embarrassing. It is normal for living science. If anything, it is encouraging. It means there is still room for genuinely transformative thought. Not every generation gets to inherit an open problem this deep. And then there is wonder, which I think deserves to stay in the room even after all the hard conceptual work. Wonder is often mistaken for vagueness, as though to be rigorous one must become emotionally colourless. But the best physics has always balanced the two. Wonder is not the opposite of understanding. It is what remains when understanding sharpens enough to reveal how much structure there is to understand. The Planck mass is a wonder-producing idea precisely because it is so exact. It is not a mystical cloud. It is a definite scale built from definite constants, pointing toward definite tension in our current theories. The more clearly one sees that, the more remarkable the whole situation becomes. Here is this scale, born from relativity, gravity, and quantum action, quietly telling us that the deepest fabric of the world cannot be fully described by our present separate frameworks. Here is this threshold, tiny in human terms, enormous in particle terms, linking black holes, the early universe, singularities, information, geometry, and the limits of measurement. Here is this one concept, the Planck mass, acting not as a final answer but as a compressed statement of unfinished reality. If that is not enough to inspire a little awe, I do not know what would be, and perhaps that is the most fitting place to rest with it. Not at a conclusion, because the subject itself has not yet earned one, but at a clearer sense of what has been learned. The Planck mass tells us that gravity and quantum physics are not separate kingdoms forever. It tells us that the smoothness of space-time may be conditional. It tells us that black holes are not side curiosities but deep clues. It tells us that the ordinary success of our theories depends on a vast hierarchy of scales. It tells us that the boundaries of physical meaning may themselves be physical. And it tells us that science, at its best, does not just gather answers. It learns how to identify the places where answers must become deeper. So now, if you're listening somewhere late at night, perhaps with the room gone dim and the day feeling pleasantly far away, it is worth noticing that we have travelled a long distance without moving very far at all. We began with a curious-sounding scale and followed it into the foundations of reality. We met the weakness of gravity, the power of quantum uncertainty, the threat of collapse, the mystery of black holes, and the unfinished search for a theory beyond Einstein and the Standard Model. And after all of that, the Planck mass remains what the best scientific ideas often are, Not a decorative fact, not a slogan, but a doorway. A very small doorway, one might say, though it opens onto an enormous landscape. And here you are now, a little farther along your own evening than when we started, living once again at the human scale where clocks tick, floors stay firm, and space-time remains mercifully smooth enough for sleep. The Planck regime is unimaginably distant from daily life, but in another sense it is never far away at all. It is woven into the laws that make everything else possible, hidden beneath the calm surface of experience like a question not yet fully answered. That, to me, is one of the loveliest things about physics. Even in the most ordinary moment, the world is still underwritten by mystery. So wherever you are listening from tonight, and whatever hour it has become in your corner of the universe, I hope this quiet excursion has left you with a little more clarity, and perhaps a little more appreciation for the unfinished grandeur of things. The Planck mass may sit at the edge of our current understanding, but edges are often where the view is best. And somewhere beyond that edge, gravity and quantum theory are still waiting to be taught how to speak in one voice.